Right, right. 15 minutes is okay.
Okay, so less than 1 hour. It's to
Less
allow.
than 1 hour.
Yeah,
Less than
yeah.
an hour. Okay, so then we should start the first session today. It's my big honor to introduce our first speaker today, Professor Serena Di Pierro. As I mentioned before, as usual, we make a short presentation of the speaker, so I will proceed. Professor Serena Di Pierro is an Italian mathematician whose research involves partial differential equations, the regularity of their solutions, their phase translations, non-local operators, and free boundary problems with applications including population dynamics, quantum mechanics, crystallography, and mathematical finance. She is professor in the School of Physics, Mathematics, and Computing at the University of Western Australia, where she heads the Department of Mathematics and Statistics. So, Professor Di Piero, it's a big honor to have you here. So please start with your presentation. Thank you very much.
Okay, so thank you very much, Duman. As I said, it's a great pleasure for me to be here with you online. And I'm very sorry, really, some people have to wake up very early. I know it's always complicated to organize like these online conferences and organize like and accommodate like good time zones for everybody. So thanks for being here. Yeah, so I'm going to talk about, I'm trying to describe, let's say, from scratch, this phenomenon of phase transition or phase coexistence. It depends if you are a mathematician or a physicist, but it's essentially the same phenomenon. And then I will try to describe from scratch, from the phase transition model as it was introduced by Landau. And then I will try to give you some, let's say, more recent results about long-range phase transitions, which is essentially the field where I work. Okay, so as I said, phase transitions, as we intend them, have been introduced by Lev Landau, who is this guy here in the picture, and so yeah. Essentially, the idea is that you have a given material, maybe in a given container, and this material can take different phases, say 2 for simplicity, and you want to try to describe how these 2 phases somehow coexist, okay, in, say, a given environment. And this is a very complicated topic of investigation, combines like perspectives coming from different fields of mathematics, like statistical and also physics or statistical physics, and science in general, I would say. So mathematical analysis, but material sciences and so on. So many areas like of investigation. And the setting may be slightly different according to the case that you are actually considering. So I think the one that you are most used to is the coexistence, for instance, of I don't know, water. Let's say water in different states, so ice and water. So we are familiar with changes of state related to melting, freezing, vaporization, and condensation. But there are also other situations in which these phase changes, phase coexistence occur, which is, for instance, when you have conductors and they move to a state of being conductor to a state of being superconductors. And that's maybe, that's also very much investigated because there are many like interests in that direction. So in any case, like a common trait in the study of, in the understanding of phase transition is essentially to describe a given system in terms of some relevant physical quantities that you have, that you may consider. For instance, temperature. We will mostly focus on temperature for this talk, but also pressure, volume, and magnetic moment. So different physical quantities according to the situation that you are dealing with. And so we will see that the energy of a given system is somehow described, so the ability to perform some task, okay, for the system. Sometimes there is what is called the latent heat. So sometimes the system wastes somehow some energy changing phase in the form of heat. And that's what is called latent heat. And I guess we are somehow familiar with that. So the free energy, for me, is going to be somehow the useful energy. So the difference between the internal energy of the system, the full internal energy of the system, and the energy that is actually wasted, through this process, to perform work. And so minimizers of the energy, or in more generally, one can look at stable critical points, for me correspond to observable states of the system. And okay, so this may change according to the temperature. So this is also something that somehow we have experience with. So usually when you have very high temperature, this corresponds to a more disordered phase, while usually at low temperature, somehow things get more ordered. So you see some more structure in there. So this phase coexistence may vary according to the variation of a given parameter, say, for instance, the temperature in our situation. And for instance, if you look at a phenomenon like magnetization, one can see that magnetic materials have basically no permanent magnetic moment above like a critical temperature, which is called the Curie temperature, which of course depends on the materials, and is, for instance, 570 degrees Celsius for the usual magnetite. But if we go below this critical threshold, this critical temperature, the atoms somehow tend to align, and they behave like little, like tiny magnets, so they spontaneously align, and the magnetic materials show at this point a permanent magnetization that is oriented in a given direction. So we have this structure of more disordered phase above a certain temperature and a more like structured situation below a critical temperature. And then, of course, the formation of these magnetic domains where spins are now aligned produces some interfacial energy between like different magnetic domains. So we have this sort of domain segregation with some phase separation at this point, which in our experience is as small as possible. Okay, so phases somehow coexist, and so there is a sort of segregation between phases with a segregation that is possibly very small. So let's try to understand this more mathematically. So to model this phenomenon of phase transition, one can consider a given order parameter, a state parameter eta. And eta describes how every point of the system is organized with respect to a given notion of phase. So we give a notion of phase, say, I don't know, water and ice. So I have two phases, water and ice. And I want to understand, I assign a parameter like, a parameter eta to a situation, so to every point of the system according to this notion of phase. Now, this parameter can be whatever, like a scalar, a vector, a tensor, according to different situations, but for us, so we will consider only the case of a scalar function. So for us, the simplest case. Okay, so what Landau did, so essentially Landau looked at two different types of phase transition that we will see in a moment. So first of all, he said, okay, I assume that the free energy presents a Taylor expansion according to this order parameter, the state parameter eta, which is like this. Okay, so it has a Taylor expansion relative to this parameter eta with some coefficients, A0, A1, A2, and so on, that depend on the relevant physical quantity. So for us, it's going to be depending on the temperature. And yeah, so we suppose that they depend on the temperature of the system. So these parameters, these coefficients, A0, A1, A2, depend on the temperature of the system. Okay, and Landau said, okay, I can construct two models for phase transitions depending on the presence of latent heat. So if there is latent heat, I will look at the specific form of this expression here in red. If there is no latent heat, maybe I will have another expression. Okay, so we will look at these two different models. So for instance, if there is no latent heat, So Landau focused on the specific case of symmetric energies with respect to the order parameter. So up to, let's say, neglecting like lower order terms, we are looking at an energy of this form, okay, which is symmetric with respect to eta. And okay, one has to assume some conditions. So you see, depending on some critical temperature, so some conditions on the parameters, on the coefficient, sorry, 0 to A4, depending on this critical temperature, because we want to see different things according to the critical temperature. And then one can check, this is not a difficult computation, that if we are above the critical temperature or equal to the critical temperature, the only critical points of the free energy is 0. Okay, the only critical point is 0. If we are below, so if we get to a more like ordered state, we have actually 3 critical points. So there are 2, so there is 0, and there are 2 additional symmetric, of course, critical points. Okay, so, and moreover, and we will have a picture, so this is probably will be more clear from the picture. When we are above the critical temperature, the critical point 0 is a non-degenerate minimum. Is a degenerate minimum at the critical temperature. It becomes then a maximum when we go below with these 2 non-degenerate minima, plus and minus whatever it's under the square root. And so this is the picture. Basically, when we are above the critical temperature, we have something like this blue parabola here, so 0 is a minimum. Then at the critical temperature, we have something like, for instance, the yellow curve here, where basically 0 becomes like a degenerate critical point. And then when we go below, so this the blue line here at the bottom of the picture, 0, we see that 0 becomes now a maximum, and we have 2 minima for our energy, which are basically at the same level. So these are like the 2 phases that are generated and that coexist because they are both minima at the same level of the energy. And so this is the bifurcation diagram for the minimizers. So we have 0, 0, 0, and then we generate 2 symmetric minima below the critical temperature. And these are the graphs of the free energy as function of the temperature. So we compute the free energy at the minimizer. So now they are functions of the temperature. We see that both the free energy and its derivative are continuous functions. But you see the first derivative. So let's say the second derivative will have a jump at this point here. Let's say the critical point, which is the critical temperature in this picture, essentially. And so what this is called, that's why this is called second order theory of phase transitions. Now this is a bit misleading maybe if you come from, the field of PDEs, because second order means something for us. But in this situation, second order, I think, means that there is a jump in the second derivative of the free energy as a function of the temperature, okay? And here there is basically no latent heat, so no waste of heat of energy during the phase change, because essentially the first derivative is continuous here. So we will see in the other situation, this will not be continuous, and that will correspond to presence of latent heat, okay? Okay, so this is the first case. And this is what now we will call actually first order. So in first order, again, this has nothing to do with PDEs, but it has to do with the jump in the derivative of the free energy. That's why it's called first order, because we will see it as a jump in the first derivative of the energy. Okay, so now there is latent heat, and Landau described this situation in this way. So we have a model in which 0 is the observed value, so the minimizer of the state parameter above the critical temperature, but below there is a new stable phase that arises, okay, at some eta star strictly positive. And okay, this is produced by a free energy of this form. You have to assume some condition, but I don't want to linger too much on this. One has to check that this condition gives rise to the situation that we are describing. But this is the picture. I think it's easier to understand it from the picture. So The free energy corresponding to first order phase transition is what is depicted here. So you have, so if you are above the critical temperature, you have just zero. Okay, so we have to look just maybe at 0 plus infinity, let's say. So 0 here is the only minimizer. Then you see at some point something happens, and there is, if you look at this yellow line, yellow curve, there is 0, and there is also an additional minimum of the energy at the same level, so at the critical temperature. And when you go below, basically you have the formation of another phase, which is here, which is now the minimizer, which is actually below the level of 0. Okay, so one can look at the form that the minimum takes when you are below the critical temperature, and one can draw the diagram for minimizer. So you have 0, 0, 0 above a critical threshold, which for this picture is essentially 2. Okay, this is just for the sake of making a decent picture. And then at the critical temperature, now you have 2 minimizers, so 2 points here. And then when you are below, you have just 1 again. Okay, so basically what we observed in both situations is that there is at some point the coexistence of 2 phases. For second order, it was below the critical temperature. If you remember the picture, we had this symmetric curve with 2 minimizers, 2 symmetric minimizers. For first order, at the critical temperature, we had 0 and some other minimizer. So we have 2 stable states that coexist. So it is something that we can observe. Now, how the question, and the important question is, how are these 2 different coexisting phases separated? How do they organize themselves? What is the geometry of the domains corresponding to each phase? So this is what we want to try to understand. Okay, so in principle, if we just rely on this, on the discussion that we have done so far, we have this, when we have 2 minima of the free energy, they occur at the same level, then basically, from the energetic point of view, any configuration in which any point, like of the system, lies in any of the 2 phases is as good as any other, because we are sitting on the minimizer. So I can say if the 2 phases are given by +1 and -1, any situation in which every point is at either +1 or -1 is as good as any other. Okay, so this doesn't tell much about how they organize themselves, how phases organize themselves in a given container. And this is also a bit in contradiction with what we experience, like in our everyday life, because in many phenomena, the change of phase occurs actually in very specific regions. Look, for instance, at these pictures, where, so this is a picture of silicon steel, and there is an external magnetic field. So basically, the atoms behaves like these little magnets, and they basically align spontaneously themselves. And you see that you have essentially these 2 phases. One is the maybe whitish one, and the other one is the black one. And see, okay, these walls are moving according to how you tune the external magnetic field, which is increasing. But you see that the phase separation is not random, like a random curve. It's actually a very straight line everywhere. Okay, so it's very, it's not wild. It's very, very regular. Okay, so there is something else. The phenomenon is not described just by saying, okay, any minimizers of this free energy is fine. There is something else there. And yeah, this is another picture related also to phase coexistence. Okay, so one has to add something else to the energy. Okay, we may have, say, a potential saying, okay, my points prefer to sit on minima of, say a given potential, say my points would like to sit on the 2 phases, which for us, for the remainder of the talk, are going to be plus and minus 1. But there is something else. And this something else is some sort of interaction energy. So you want points nearby, maybe not only points nearby, to interact. So I want that if this point somehow, if this atom align itself, so also atoms nearby will feel this alignment and will do the same essentially. So we don't want this abrupt phase changes because this is not what we see. So one can add an interaction energy of the form. So this is a double integral of eta x minus eta y squared times a given kernel that we can choose according to our specific situation. And now if I want to minimize this energy, of course I want that eta of x minus eta of y is as small as possible. So you say if eta of x is at +1, maybe eta of y at least around x will try to stay at +1. So this will penalize this abrupt phase changes of phase. So we assume the kernel to be symmetric under translations and rotations. So we get like a simple model that we can deal with mathematically. So if we do that, K is essentially a kernel, actually kernel of the distance between the 2 points. And then now if in first instance we assume that the kernel is short range, so say it vanishes whenever the distance between 2 points is bigger or equal than rho. So if I am at point x, this point x will feel the presence of points y in, say, a ball B rho centered at x, and that's it. Okay, so now the kernel is short range, so this is an integral in B rho. And in first approximation, so if rho, say, is small, this is nothing but essentially the integral of the gradient square, which is something that we are very familiar with, plus smaller order terms, and the constant is a constant depending on the kernel, say. And so accordingly, the interaction term for short-range interaction, so if we assume this, we can say that this interaction term is approximated by the classical integral of the gradient square. Okay, so for short-range interactions, at the end, one can describe the coexistence of two phases for the situations of interest, so first order phase transition at the critical temperature, and second order at the critical temperature or below the critical temperature, via this energy function. So now we have the interaction energy that we have just described, so an integral. So suppose that we have a domain omega, that we are looking at the situation in this given domain, and eta now describes, okay, the phases here. I have this integral of the gradient square, so what we just described. So this should penalize these changes of phases for eta. And then we have a potential energy. So W now is a double well potential, say with minima at plus and minus 1. So plus and minus 1 are the two phases, favorite phases of the material. And W is a potential that is, say, strictly positive everywhere, but at plus and minus 1 where it is 0. So my material prefers to sit at these two pure phases, plus and minus 1, but of course it has to be careful because there is also this penalization term. So I don't want to change from plus 1 to minus 1 whenever I like. There is something more in this. So this is the energy that one can look at. And in this case, the phase separation, so as we said, and as we observed also in the picture, is not as wild as possible. It is actually dictated by the surface tension. And what the material tries to do, tries to make the interface to be like a codimension one surface with the least possible and minus 1 dimensional area. So with the least possible perimeter. So like straight lines as we saw in the pictures before. Now, how can one see this like very, very, let's say, roughly speaking? So if one introduces a parameter, so one can rescale a bit the picture in such a way that the main term is the integral of W, and the integral of, which is actually like the important term in a sense, that one that tells us that the system is going towards the coexistence of these pure phases, plus and minus 1 and nothing else. And then we add this penalization. So now we see this mostly as a penalization. There is an epsilon term in front. And if you do Cauchy-Schwarz here, now you see that this term is bounded by this integral here. And then you can do area formula, and you can write this integral in omega as the integral from -1 and 1 of so in d tau of the integral along the level sets of eta of whatever remains, the potential. And now you see whatever is in here is essentially so the integral, this integral here in omega is just giving us the perimeter, essentially, if things are nice, but the Hausdorff, the n-1 Hausdorff dimension measure of the level set of eta. Okay, now we have done like a bit of so we can think somehow that minimizers of the energy are related to minimizers of the energy here, and so the material will try to somehow to minimize the interface between these pure phases by minimizing the perimeter of this object here. Okay, morally. Now the thing is, it's not as, I mean, it is like this, but this is not enough of a justification because there is a Cauchy-Schwarz inequality here. So you needed maybe Cacciopoli and De Giorgi to check that actually one can do like a rigorous argument out of it, and one can prove essentially that for small epsilon, so the minimal energy is expected to be related to minimizers of the perimeter, where the perimeter is this object here with some constant depending on the potential, and the set E is essentially the set in which the order parameter eta is basically +1, and the complement is when it is -1. So the situation is like this. So we have these two pure phases, +1 and -1, they separate and they create an interface in between them. And this interface is done in such a way that it tries to minimize its perimeter. Okay, so it's n-1 Hausdorff measure. Okay. Okay, so this is what happens for short range. So we have to keep in mind that minimizers of the energy are connected to minimizers of the perimeter. And so if I want to try to understand minimizers of this energy, of the free energy, one should somehow try also to understand the minimizers of the perimeter. Now, what happens, one can also consider if long-range interactions. Okay, so in this situation, you cannot perform like this gradient approximation because every point now interact with any other point. And so we can say that, so we leave the potential term the same. So we have the integral of the double well potential that favors the formation of the pure phases, plus and minus 1. But now we have this sort of long-range interactions, okay? We have this kernel, which is a double integral. And this double integral now sees the interaction of every point with any other point. Not exactly in the sense that I'm integrating in this cross-shaped set. So this cross-shaped set is omega times omega, then the complement of omega times omega, and then omega times the complement of omega. So the only interactions that I don't take into account in this minimization is the interactions between points outside omega with points outside omega. And this is simply because somehow I will do the minimization assuming some boundary or exterior data. So that interaction outside is essentially the same for every competitor. So I don't put it there. And don't worry too much about like the 1/4 in front. This is just a normalizing constant that I want there in such a way that when I do the minimization of the energy and I get I get an operator which is in the form that I want. Okay, so I don't have additional like constants. Okay, so yeah, the intuition behind the set, this cross-shaped set Q omega, is that we are prescribing the order parameter outside omega, which is like the global counterpart of prescribing eta just along the boundary. So if we look at long-range interactions, we want to know how every point interacts with any other point. So we need to define also our fit parameter outside omega. Okay, so that's it. So the boundary of omega is replaced by the complement of omega, if you want. Yeah, and so the energy function accounts for all configurations which involve the values of the state parameter in omega. So you have at least one point has to be in omega. Because, yeah, as I said, when I am outside times outside, then that's the exterior datum that is given by the problem. It doesn't influence the energy minimization. Okay, so special cases of kernels that we want to take into account are the ones which are like positively homogeneous of some degree d. So, for instance, such that k of tz is t to the power d kz. And if one actually checks, if you want to have finite energy, d cannot be anything. It has to be in between minus n minus 2 minus n. So d, we will write d as minus n minus 2s with s in 0, 1. Okay. Now, in this situation, the limit interface is again related to minimizers of some sort of perimeter functional. The thing is somehow more complicated than before, because when s is equal or above 1/2, we still recover the classical perimeter. So minimizers of our energy are related to minimizers of the perimeter, like before, even though it's more complicated to check, because now we don't have before we did Cauchy-Schwarz and co-area formula. Here is trickier than before because our original energy is non-local. But when S is below 1/2, minimizers of the energy are related to minimizers of a non-local version of the perimeter. Okay, it's still a perimeter, but a non-local version that we will see in a second. Okay, so now if you want to understand minimizers of your energy, you have to try and understand minimizers of, say, the perimeter, which are somehow understood, and minimizers of the non-local perimeter, which are way less understood than minimizers of the classical perimeter. So the situation when you are below S is somehow trickier because you have to understand this non-local perimeter, which is somehow a very new, a very new object. But the nice thing, in a sense, is that when you are below 1/2, you are in what we will call like the strongly non-local or genuinely non-local regime, which means that even at this scale, like even if you change scale, you still see a non-local object. Okay, so while when you are above 1/2, you start with the non-local energy and you end up with the surface tension, the classical perimeter. Okay. So I'm gonna focus. Okay, so this is let's start the second part of the talk, which is maybe a bit more mathematical, more rigorous in a sense. I'm gonna try to give you some results that we obtain in this set, or that were obtained in this setting. So we look at the operator now associated with the energy. So if you do the variation of the long-range energy, you end up with the non-local operator. And with our assumption, kernel symmetric, kernel homogeneous, with D, remember D here is minus n minus 2s, we end up with what we call the fractional Laplacian. So this operator, this non-local operator. Now, if you're not familiar with this operator, like the first time that I saw it, it looked pretty ugly to me, I would say, because like the Laplacian is much nicer, right? The Laplacian is just, you take derivatives, it's beautiful, we can do on any reasonable function. Okay, this one is more complicated, we don't really understand it, but the idea, essentially you have some sort of, it's some sort of incremental quotient that you have, but of order 2s rather than 2. Okay, so it's an operator, say, of order 2s rather than 2, and you are averaging out in Rn. So you want to see interaction of points everywhere, okay? So for me, S here is gonna be between 0 and 1. When S tends to 1, you see 2s tends to 2, and indeed the fractional Laplacian becomes essentially the Laplacian, converges up to a suitable renormalization to the classical Laplacian. So it's a reasonable definition. And we will look also at the specific case of the non-local Alenkana equation. So remember, we had this energy with like this long-range interaction energy, which would give us the fractional Laplacian. And then we have a potential, and if you choose the potential to be the classical Alenkana potential, you end up with the Alenkana equation, which is this here. So this comes from a potential which is 1 minus u squared, which is the Alenkana potential. Now, if you take a minimal solution, so a solution of the equation that is a minimizer for the energy, you rescale it, right? Which is what we did before when we introduced the epsilon. And this is called the blowdown. The rigorous statement of what we said before, that minimizers of the energy are related with minimizers of perimeter, is this one. So if you take your energy, your minimal solution, you blow it down, so you rescale it. This u epsilon, as epsilon goes to 0, converges to some step function. Okay, so this is like this is 1 if the point is in the complement of E, and -1 if the point is in E. And this E is not a random set, E is a local minimizer for the classical perimeter when S is above 1/2, and the fractional perimeter when S is below 1/2. In the classical setting, so this is essentially the fractional version of the so-called modica mortola result in the case of the Alenkana equation. So what is this fractional perimeter? Okay, so what is that? The fractional perimeter was introduced now some years ago by Luis Caffarelli, Jean-Michel Roquechot, and Ovidio Savin. And it looks, so you can imagine it's non-local, so like for the fractional Laplacian or for the long-range interactions, it has to account for interactions between like every point with any other point. So if I take two disjoint subset of Rn, and here S now is only below 1/2, which is the regime that we are here, that we are interested in. We take this interaction between two sets, which is given by our interaction kern, because it's the integral of our interaction kern. And the fractional perimeter is essentially the interaction of the set E with its complement in such a way that also omega is taken into account. Okay, so this is to say that I let E interact with its complement, like we did before for the cross-shaped domain, as soon as the point lies in omega. So I don't look, so I let E in omega interact with the complement of E. So E in omega interacts with the complement of E in omega and the complement of E outside omega. But if I am outside omega, this interacts only with the complement of E inside omega, because outside we don't care. That's fixed data. And so this was introduced in 2010. Yeah, again, this counts the interaction of E and the complement with respect to the reference domain. Now, like for the fractional Laplacian, now if you send S to 1/2 and you rescale suitably the fractional perimeter, it converges to the classical perimeter. Okay, so we recover the classical perimeter. So you see there is a bit of a cross limits here. So this converges, U epsilon converges to minimizers of the classical perimeter when I am above 1/2, the fractional perimeter when I am below. And when S goes to 1, the fractional Laplacian converges to the Laplacian, and the fractional perimeter converges to the classical perimeter when S goes to 1/2. So they match well somehow. Okay, now critical points of the perimeter possess zero fractional mean curvature. This is similar to what is true, to what holds true for classical critical point of the classical perimeters, which satisfy mean curvature equal to 0. This is again uglier than the classical mean curvature. It is essentially the same difference with respect to the classical mean curvature as the difference between the fractional Laplacian and the Laplacian. And people have looked at that. You can consider associated like the associated geometric flow, motion by fractional curvature. I quoted just a couple of references here, but the literature is becoming larger and larger on this topic. Okay, so now more specifically, so now I'm going to focus, I want to focus essentially on the case in which S is in between 1/2, which I will call genuinely non-local regime, genuinely non-local case, because this is connected now to the fractional perimeter. And I'm going to look at a slightly more general operator than just the fractional Laplacian. I'm going to introduce an anisotropy here. So you can look at anisotropic non-local operators. But if you're too bothered by this additional complication, just think about the fractional Laplacian. Forget about mu. Mu, take it to be equal to 1, and all the results would be true in the case of the fractional Laplacian. Would be as good as in the case of the fractional Laplacian. And you can also consider more general anisotropic operators. But again, we can just think about the fractional Laplacian if we like. What about the nonlinearity? Okay, we can take into account the Alenkane nonlinearity, so u minus u cube, and it would look more or less like this. You can also take into account more general nonlinearities as soon as f of minus 1 is equal to f of 1, which is equal to 0. So these two have to be equal to 0. And also we need f to be decreasing when we are close to the two pure phase. So there is this little parameter kappa that tells me that when I am, say, in this interval 1 minus kappa 1, the nonlinearity is decreasing, and similarly, when I am in between minus 1 and minus 1 plus kappa, the nonlinearity is decreasing. Apart from that, it can do anything that it likes in between. The reason for this additional assumption is that at some point we need to use maximum principles in that regime, so we will need basically some sort of ordering from the right-hand side of the equation. Okay, so the classical example, and this is what we can have in mind, is Alenkane type equation, so u minus u cube. And so this is how our equation will look like, L of u equal to f of u. Again, L can be for the fractional Laplacian for us, and f of u can be the Alenkane nonlinearity for us. So fractional Laplacian equal to u minus u cube. That's the equation that we have in mind. And we will call the interface, so I've mentioned already this word like many times, but I will say now, from now on, that the interface of the solution u is whatever is essentially far away from the pure phases. So is the set of points where u is the modulus of u, so the absolute value of u is smaller than or equal to 1 minus kappa. And kappa was the non-decreasing parameter. Okay, so I am far away from those regimes. I'm far away from 1 and minus 1. That's the interface. And I will say that I of u, so the interface is gamma trapped in some ball, in some direction, if this happens. But never mind, this is the picture that is much nicer and also much easier to understand. So I have a given ball. I take a slab with 2 gamma. I pick a direction, omega, and I say that the interface is gamma trapped in this ball, in the direction omega, if the interface lies in this slab, in this yellow slab here. Now, of course, if gamma is bigger than r, comparable to r, I'm not saying much. BR, of course, I am containing the slab. But if gamma is significantly smaller than r, I'm saying, like, I'm giving some significant information. Okay, so it's a trapping statement. Sorry, definition. I'm trapped there. And then remember, so we are aiming at some sort of rigidity results. So if we have in mind the picture of the aluminium, the interface for us. So we have to have in mind that the interface is as regular as possible. It was like just a line in that specific case. So we aim at having solutions which are one-dimensional, at least in some dimension. One-dimensional means that level sets are flat. And level sets, remember, are related to minimizers of the perimeter. Okay, so So we are aiming at having solutions with nice level set, so as flat as possible. Okay, so one-dimensional solutions. So we say that U is one-dimensional if I can find a function, a one-dimensional function, and the direction such that U at x is actually U0 of omega times x for any x. And there is a famous conjecture by Ennio De Giorgi from 1978 that says that if I look at the classical Alencane equation, so with Laplacian, I set of the fraction Laplacian, if I have a nice bounded and smooth solutions of this equation in Rn, which is monotone in one direction, then U is 1D, at least if n is smaller than or equal to 8. Okay, so this additional assumption, this additional request, if n is smaller than or equal to 8, is connected to the regularity of minimizers of the perimeter functional, because now we understood that these two things are related. And because he knew, so the Giorgi knew that minimizers of the classical perimeter functional are smooth up to dimension 7, and then there is a counterexample to regularity in dimension 8, which is the Simon's cone. He somehow connected this to put, and then he knew the convergence result, so he knew that he knew this connection between these two things. He put these two things together and he said, okay, they can be regular, but they cannot break, like they cannot go. We cannot go like above the regularity of minimizers of the classical perimeter, and that's why we have this dimension 8 here. And so, let's say the last few minutes, I'll try to tell you a bit about what we did, so the theorems that we had in this setting related to this conjecture by De Giorgi, but for the fractional Alencane equation. So this is the first result. Obtained in collaboration with Joachim Serra and Enrico Valdinoci. If you have a solution of your equation that is trapped, say in BR for some direction omega r, trapped in this sense. So the interface is AR times R trapped, where AR is a function that goes to 0. So it's flatter and flatter at infinity. So it's trapped, but it's getting better and better at infinity. Then U is one-dimensional. Okay. So this is not yet the conjecture by De Giorgi, but it's much. I don't know, maybe I don't want to say that, but it's a very geometrical result, and it's in a sense stronger because you see there is no dimension here involved in this statement. This is saying that the moment I can say that my solution is very flatter and flatter at infinity, somehow this flatness at infinity allow me to conclude that I have actually some rigidity like close by, and so the solution is one-dimensional. And clearly, this condition has to see some dimension at some point, because we know for the Alencane it has to see the dimension because of this connection with perimeter functional. And this condition is related, so it is satisfied in some specific dimension. Okay, so that's where we will see the dimension. But this is a very general statement in principle. And it's actually stronger than the classical case. In the classical case, you wouldn't have a statement like this, because there is this paper by Delpino, Kowalczyk, and Wei that is called Transition from a Catenoid. So what they did, basically, they started from this catenoid. So the catenoid is, now this is a two-dimensional picture. You have to imagine the same picture but rotating around. And what they do, basically, they construct a solution on the solution of the classical Alencane equation, let's say shadowing the distance to the catenoid. Okay, so this solution goes towards -1 on this side and on this side, and then it goes closer to the catenoid, and then it gets to +1 inside. The thing is that the catenoid in the classical case is as a logarithmic growth. So this solution U would be trapped in a slab, let's say with log R. And if we go back to our result, if log R, so log R can be written as log R divided by R times R, So the interface would be AR times R trapped, and AR is log R times R, which goes to 0 when R goes to plus infinity, but the solution is not one-dimensional because it is constructed on the catenoid. So the same result is not true in the classical case. So somehow non-local objects are uglier in a sense, especially if you are not used to working with them. And I mean, they are ugly because, come on, integrals are more difficult than derivatives. But somehow, the fact that you have to take into account the big picture. You have to look at the global picture and look at the function everywhere. Somehow, this gives you more rigidity. Okay, so you can prove a result that is stronger than the result in the classical case. Okay, let me finally go. Okay, let me skip this. So this is essentially a related result to the Giorgi conjecture. So if I have a fractional Alenkane equation, a solution of the fractional Alenkane equation, monotone, if I assume this additional condition of limits at plus and minus infinity, when n, you see now we have the dimension, when n is below 8 and s is sufficiently close to 1/2, then u is one dimension. And this is again related to the regularity of fractional minimal surfaces, because when S is very close to 1/2, the fractional perimeter converges to the perimeter. We know the regularity of minimal surfaces, and non-local minimal surfaces inherit the regularity. When S is very close to 1, they inherit the regularity. And so basically we can prove this result when S is sufficiently close to 1/2. In dimension 3, we can do better. We can actually prove the Giorgi's conjecture in the fractional case, and this is what we did with Alberto Farina and Enrico Valdinoci. In dimension 3, you have a monotone solution of the Alenkane equation that nu is one dimension. So this is the Giorgi's conjecture. And to finish, maybe I'll finish here, but let me just give you a slide of where we are sitting in this big picture. So the fraction of the Giorgi conjecture was proved in dimension 2 when S is equal to 1/2 in 2005 by Xavi Cabré and Joan Sola Morales. And then a few years later in dimension 2, like for any S, there are two papers with two different strategies by Yannick Cyr and Enrico Valdinoci, by Xavi Cabré and Yannick Cyr. And then dimension 3 was attacked by Xavi Cabré and Eleonora Cinti, and they did first the case n equal to 3, S equal to 1/2, and then the case S about 1/2. And then this is our result with Alberto. So dimension 3 is below 1/2. So now dimension 3 is also well understood. And then there is only one result, which is due to Alessio Fegali and Joachim Serra in dimension 4, in the specific case S equal to 1/2. And yeah, there would be more to say because there are also additional conditions that you can impose, like this condition of limits that you can impose to prove the conjecture also like in other situations. And so if you assume that the limit is uniform, so plus and minus 1 are essentially two pure phases, right? So we know that they are the minimizers of our energy. So the fact that you know the profile at infinity helps in the proofs. So that's why you can get the result. So if you assume uniformity, then the solution is one-dimensional in any dimension. Okay, so here we beat also the regularity of minimal surfaces. Yeah, this was our result with Joachim and Enrico, and yeah, when S is about 1/2, this also has been done by Ovidio Sami. Okay, so there are like, if you look at this slide, there are like many situations where we don't have the results. So in dimension higher than 4, we don't know. We don't have counterexamples in dimension 9. So it's a big open question in the non-local setting. But I think my time is over, so I don't have time to like give you like ideas of the proofs. But I think it's better like this. Yeah, I can stop here. And if you have any questions, I'm happy to try to answer.
Okay, Professor Di Piero, thank you for your nice talk.
Thank you. Thank you.
And sorry, I thought I have the the mic open. We're now
No worries.
we're now open for questions. Remember, you have a question for Professor Di Piero. You can raise your hand via the Zoom system, or you can write it in the chat. Okay, maybe let me see if we have some question on YouTube or the auditorium. I think no. So if not, Professor Di Piero, I want to thank you again.
Too early in the morning, baby.
No, but maybe,
No, but like
maybe not.
if you have questions later on, or if you want me to share the slides, please feel free to send me an email, and I'm happy to answer or to have a discussion.
Okay, Professor, thank you for supporting this event. I think
Thank you very much.
It was very interesting, and success, your the rest of your career.
Thank you.
Bye, Professor.
Bye bye.
Our next talk is by Professor Barilari, but it's in an hour. So we having a break now, a 1 hour break, and we will come back for Professor Barilari. Today is the same link of Zoom. We had a problem yesterday, but now we recovered the links. So the rest of the event today and tomorrow will be at with the original Zoom link. Okay, so see you in an hour. Bye.
Bien, ve, me quedé
Professor David, are you there?
Hello,
Hello, hello. It is a pleasure.
my pleasure. So I just tried the Zoom link to see if everything was good, but I will connect maybe later because I see there is a time still.
Yes, it's okay. Maybe if you can try to share your screen just to check everything is okay.
Ah, sure.
How do I pronounce your name? David? David
Ah,
Vale?
it is okay. Davide in Italian is Davide, but you can say
David.
David.
Okay.
No problem. So I'm just trying to take my slides. Okay, so they're there,
So, yeah.
and then I can try to share. Acrobat. You see this?
Yes, perfect.
Very good.
Okay, nice. So we'll see you in about 40 minutes, maybe.
Perfect. See you later.
Thank you for accepting our invitation, Professor. See you
Thank you.
later.
See you later.
Bye. Okay. Hi again, everyone. Can you hear me? Hi, Professor Saladini. Hi, David.
Hello.
Okay, we are going to start now. Professor David, please share your screen.
Can you see my slides?
Yes.
Thank you. I will try to put it full screen and then you'll tell me if this works.
Okay.
So where is it? View full screen. Can you still see?
Yes. Please. Okay, this work.
Works. Okay.
Okay. Okay, today we are honored to have Professor Davide Barilari with us. He's a full professor at the Department of Mathematics at the University of Padova. His academic career spans fields such as sub-Riemannian geometry, geometric control theory, and optimal transport. He's going to present the talk titled Unified Synthetic Ricci Curvature, Lower Bounds for Riemannian and sub-Riemannian Structures. I think this is an interesting topic for me, and I hope you all enjoy. Welcome, Professor, and the audience is yours.
Thank you very much. I hope you can hear me correctly. And so thanks to the organizer for the nice invitation to this event. Very interesting. So I'm pleased to talk about my work here. So I will tell you a bit about this last work of a series of work concerning say a definition, a synthetic definition of curvature for sub-Riemannian geometry, and actually sort of unification of the notion of Ricci bound for Riemannian and sub-Riemannian geometry. I will be more precise. So I will start with some motivation after saying that this is a joint work with Andrea Mondino and Luca Rizzi. In particular, I will emphasize the result of this paper here, and I will also mention some previous results obtained by Luca Rizzi in those two papers. So I will start with some recap. Please do not hesitate to interrupt me if you have any question. So I want just to recap a bit what is okay, I removed just the control, sorry. I want to recap what are comparison theorems in Riemannian geometry, so just some known result. Comparison theorems are results where you have bound on the curvature and you obtain bound on the geometry. One of the classical theorems is the Bornemeier's theorem, which is saying that if on a Riemannian manifold, you have, say, of dimension capital N, and you have a control from below of the Ricci curvature, so the Ricci is bigger or equal than K, then you can say that the manifold is compact and you have a bound on the diameter. Essentially, the diameter is less or equal than the diameter of a sphere of the corresponding curvature K. So you have here the diameter of the sphere who has Ricci curvature K. You have a similar result if you look to Bishop theorem, saying that you can bound the volume of a ball in your manifold with respect to the volume of a ball in a constant curvature space equal to K. So here I'm just recalling that the diameter of a sphere with constant Ricci tensor K as the diameter, which is the number you get here. Okay, so just to have an example, on the unit sphere S2 as positive curvature. So if you look to a ball on the sphere, which is the object here in blue, you can compute the area of the blue zone. It is the volume of the geodesic ball. It is less or equal than the ball in the Euclidean plane, because the curvature is bigger than 0. That is the curvature of the Euclidean plane. Okay, so to put these things into perspective, you start with these results in Riemann geometry, comparison theorem. So it is very interesting to have information about the control under Ricci curvature to get some more information about the geometry of the space. These results have been extended by the Chigre holding theory to what are called Ricci limit space. These are singular spaces that can arise as a limit of Riemannian manifold. And later in 2006, the Lot-Sturm-Villani theory, in some sense, permits to give a synthetic notion of Ricci curvature bound in metric spaces. This is defined through optimal transport and permits to give a notion of what is bound on the Ricci curvature on a metric space. And essentially, this class of CDKN spaces is the class of metric spaces with Ricci curvature bounded below by K and with dimension less or equal than N. So K plays the role of curvature bound, N plays the role of dimension bound. The nice properties of this theory, this synthetic theory on metric spaces, is that this is consistent with the classical Riemannian theory. It contains limits, so you have a sort of compactness and stability property, and you can have a unified viewpoint of the smooth and non-smooth case. So there are nevertheless some interesting limits of Riemannian manifold which go out of this class. For instance, if you take on R3 this three-vector field I showed here, and you take the Riemannian structure which depend on epsilon, such that the three-vector field define an orthonormal frame, what you can see is that you can make sense of the limit for epsilon going to 0 of this Riemannian structure. You see that when epsilon is 0, this vector field is killed, so in some sense the limit is no more Riemannian. But for instance, if you think in terms of the cometric, so the inverse of the metric, the Gij with the Ij upstairs, or if you wish, the Hamiltonian, which is written in this form, actually the inverse of the metric, depending on epsilon, converge for epsilon equal to 0. So for epsilon going to 0, converge to some limit matrix, which is no more invertible. So in some sense, you have the inverse of the metric, which converges to something which is not invertible. And so it means like if the inverse has one eigenvalue plus infinity. This is related with the fact that the vertical variable now costs plus infinity. The movement in this direction costs plus infinity. So the crucial point is that you have a non-commutativity property. The first two vector fields you have here are not commutative, and their Lie bracket is actually the third direction. So you can see that thanks to this property, you get a nice limit metric space when epsilon going to 0. This limit space is the so-called Heisenberg group, and this is a space where you have a constraint on your motion, so you are forced to move only in the two directions given by x1, x2, and the fact that your x3 is killed does not mean you cannot move in this direction, but since it's a Lie bracket, you can move in the direction z by combining movement in the direction x1, x2. This goes back to the definition of Lie bracket. The interesting point is that the sequence of curvature, so if you look, for instance, to the Ricci curvature, associated with the metric epsilon, is unbounded from below. So if you take a vector which is in the span of the first two vector field, the Ricci epsilon in the direction of v goes to minus infinity. So this limit example go out of the theory of Lot-Sturm-Villani. There is no uniform bound on the sequence of these metric spaces. So this limit spaces is the say toy model of sub-Riemannian geometry, and it could be interesting to ask ourselves what happens in this limit space. Let me anticipate, and then I will be more detailed, that so you get some structure called sub-Riemannian structure or sub-Riemannian manifold. There's a limit of Riemannian manifold. the curvature, the Riemannian curvature, is unbounded at the limit, and you can prove actually that this sub-Riemannian manifold do not satisfy the theory of Lossum-Villani. And so this has been proven in different steps in the literature. In 2009, Nicolas Jouillet proved in the first example that the Heisenberg group does not enter in any of the class given by Lossum-Villani. And later it has been proved that nevertheless, even if we are not in this class, the transport admits some nice interpolation inequalities. Okay, I will go back to this later. So a question is whether it is possible to build a theory, a synthetic theory, which contains both Riemannian and sub-Riemannian geometry, even if this sub-Riemannian case go out to the classical synthetic theory. So this is not only our question, it was also somehow suggested by Cédric Villani in his Bourbaki paper of 2017. And here it is written in French, but essentially it is asking whether we can treat bioptimal transport in a similar way than the CD spaces. Here it is written CD star, it is a modification, by using different distortion coefficient, which are called beta Kn. And so he was hoping for a great unification, okay? Including all Riemannian, Finsler, and sub-Riemannian class. So I will speak about this and I will try to be more formal. If you have questions, please don't hesitate. So I will recap a bit the Riemannian situation. I will speak about the difficulties in the sub-Riemannian setting. I will try to make a link with the contour theory, which you should have seen also yesterday in other talk, and I will briefly present our novel approach. Let's start. So we focus on this object, which is called distortion coefficient, which was appearing also in the text of Villani. It is built as follows. You are in a Riemannian manifold, you take the Riemannian volume, and given 2 points x and y, you fix a point x, and around y you take a geodesic ball, which is denoted by BRY, and then you shrink to x through geodesic. So you connect x with all points in the ball around y, and you build an intermediate set, which is denoted ZT x BRY, and this means all point at time t built by connecting x and a point in the ball around y by geodesic parameterized in time 0, 1. Okay, so you have an intermediate set. So this makes sense if your x and y is out of the Decathlon, because in this way the geodesics are unique. You should notice that beta at t equal to 1 is 1, at t equal to 0 is 0. In Rn by homotety, it's very easy to see that this does not depend on the point, it's just t to the power n. And in general, since we look to the lim sup when r goes to 0, so you are shrinking the radius to 0, you get something which will be concentrated, say, on the trajectory connecting x and y. When you have a bound on the curvature, you can show, so for instance, in the simplest case, when the Ricci is bigger or equal than 0, you can show that this distortion coefficient is bigger or equal than the one you get in the Euclidean space. So this is a sort, again, of comparison principle. And it is very interesting to see that this is also sufficient to imply a sort of interpolation inequality, or Brun-Minkowski inequality. So the measure of the interpolating set, where now we interpolate between two sets, A and B, and no more between a point and a set. So if you interpolate between two sets A and B, then you can show that the measure of the interpolating set at time t power 1 over n is bigger or equal than 1 minus t measure of A 1 over n plus t measure of B 1 over n. So this inequality, which is well known to hold in the Euclidean space, is also implied by the assumption Ricci positive. And of course, this second inequality is stronger than the first one because you can prove the first one given the second by taking the set A equal to a point, you reduce A to a point, and be a ball with a radius going to 0. So this second is a sort of integrated version of this asymptotic one. So you can read the same thing in this notation. If you denote beta bar 0n t to the power n, so the model beta at time t associated with 0 curvature and dimension small n, you can write the inequality in this form here. In general, distortion coefficients are difficult to compute, but their interest is that if you know the bound on the geometry, you can obtain a bound on the beta, as we have seen in the case Ricci positive. More in general, if you have a bound on the Ricci of the type Ricci bigger or equal than k, then you can prove that out of the cut locus, the beta is greater or equal than the model beta associated to the space of constant curvature big K and dimension n, which is explicit. For instance, for K positive, you are on a sphere, like the one we have described in the first example, and you can compute it explicitly. It comes out of the computation with Jacobi fields, essentially. So you have explicit formula for this beta. There are formula also for K negative. It is just replacing the sinus with the hyperbolic sinus. So you have explicit computation. So the interest is to compare beta with some model beta. An interesting observation is that on the right-hand side, you have a function which depends on one variable, theta, and the argument you have in this comparison, it is the distance between the 2 points. So in the left-hand side, you have points on the manifold. On the right-hand side, it depends only on their distance. Because essentially on the right-hand side, as we were saying, you have some beta computed in a model space where, say, you have isometries, and so you can think that everything depends only on the distance between the points. Another feature is that the explicit expression of this beta, it is as follows: a function of t divided by the same function evaluated when t is equal to 1. So this reminds our construction, right? Because the beta comes as a limit of an interpolating set at time t over a set for time t equal to 1, the final set. So if you think in terms of the Brun-Minkowski condition, and you write, if you wish, a Brun-Minkowski condition with this distortion coefficient, which depends on the parameter k, you can think that this inequality could serve as a definition of what is a metric space with Ricci bound, because actually to interpret this inequality, you need only to have interpolating sets to be able to interpolate sets. So you need the geodesics to define what is the interpolating set, and you need a measure. So if you have a metric measure space, a length metric measure space, so a metric space with the geodesics and a measure, then you can give a sense to this inequality, and you can think that it is, if the inequality is satisfied for every set A and B, then the metric space has a Ricci curvature bounded from below. This is a sort of simplification, because actually you don't use this inequality, you use optimal transport, but I would avoid to go into these technical details. But say the real definition is given by optimal transport, and this is a sort of consequence. But to interpret this, we can focus on this inequality. And this inequality has all the good properties I was mentioning at the beginning. So it unifies, for instance, Riemannian geometry and Fiedler, and is also stable when you go to Ricci limits with a uniform bound on the curvature. The point is that these inequalities are not satisfied by our limit, sub-Riemannian limit, the Heisenberg group. So let us speak about the difficulties in this sub-Riemannian setting. What happens in the Heisenberg group? In the Heisenberg group, if you remember, we had the 3-vector field, but in the limit for epsilon going to 0, the vector dd zeta was killed. So it is not possible to go directly in the vertical direction. This is the expression of geodesics in the Heisenberg group. So in the Heisenberg group, geodesics to go up, so to go in the direction of z, they should first go a bit along x and y, the first two vector fields. So this is the expression of the geodesics, and for instance, you can see that so the expression of the geodesic has this feature that when t is small, the first two component goes like t, the first one goes as a t cube. And Nicolas Jouillet proved, so as I was saying, he proved that the Minkowski condition was not satisfied, the classical one in the Heisenberg group. He proved the sharp inequality that the beta t xy in the Heisenberg group is greater or equal than t to the power 5. So this 5 is related to the geodesic dimension of the sub-Riemannian manifold, which we introduced more in general for also Riemannian structure. You can think that this 5 is related with the fact that, as I was saying, the Taylor expansion here is given by t cube. So Nicolas Jouillet proved that none of that this inequality here is not satisfied in the Heisenberg group, and actually none of this inequality for any k and n. So this was inducing people to think that it is not possible to develop such a theory in this way. But if you remember, the beta kn are coefficient. Maybe I can go back a bit to show you. If you look to this coefficient, the beta kn is always asymptotic to t to the power big N. So when you raise it to the power 1 over n, it gets always a linear term, right? So the interesting fact is that Balog and Crystal and Sipos in 2016 proved a modified Minkowski inequality, which is true in the Heisenberg group. So one could think that this inequality implies that you have to choose capital N equal to 5 to have it satisfied, but actually you have to choose capital N equal to 3, the topological dimension, because you have to remember that our example is in R3, but the beta are no more linear. So that's the crucial point. The beta are no more linear, are a fractional power, 5 over 3. So you see the 5 appearing again, but it is a 5 over 3. This geodesic dimension divided by the topological one. So these observations have been somehow proved also for more general structures and not only for the Heisenberg group in more recently. And actually here you have a series of work where the author proved that actually the Riemannian condition is never satisfied where you are in sub-Riemannian geometry. So how to understand this computation? I try to give a bit of justification. If you go back to our inequality here, this inequality in particular, if you kill one of the two sets, right? Thinking to the case where you connect a point with a set. So if you put, for instance, A equal to a point, you can then raise everything to the power 3 and you get to this inequality. And we can understand it a bit because we can first move a t power 4 to the left and then to include this t power 4 within the measure by applying a suitable dilation that I will show you in the next slide. So we have to understand this inequality here. So The interesting part that when you work in this Heisenberg group is that it is homogeneous with respect to some non-isotropic dilation. Here you have this formula, which is considering a dilation which is acting differently on the first coordinate with respect to the third. So a dilation of parameter epsilon is multiplying x and y by epsilon and z by epsilon square. If you take back your expression of the geodesics, now you see that you have a similar homogeneity property like for Riemannian geodesic. So these geodesic are parameterized by two parameters, an angle theta and a parameter A, which is telling us how much you're going up in the helix, if you remember. And what happens is that if you dilate by parameter 1 over t, it is like going for time 1 along the same parameter theta, but with a parameter a which is multiplied by t. So it is a sort of homogeneity of the geodesic, which we have also in Riemannian geometry, but here the homogeneity is given with respect to different dilations. Okay, so the interesting part is that is, for instance, you shrink a ball with respect to its center, and if you dilate, you get a part of the ball which is described in this way, and which in picture is exactly the set described here, which actually has a volume which is proportional to t. So if you do this in Riemannian geometry, you get something which is essentially proportional to a constant, right? Because you shrink to the ball, but then you dilate and you get again for t small the same initial ball. Okay, so in 2019 with Luca Rizzi, we could prove a statement linking the three fundamental properties we have been discussing up to now. So it is equivalent to have a bound on the distortion coefficient, beta txy bigger or equal than t to the power n, an inequality for shrinking a set to a point, so-called measure contraction property. So it is equivalent to have that the measure of the contraction of a ball to a point is bigger or equal than t capital N measure of B. And this is equivalent to the Brun-Minkowski inequality, where you have small n as a dimensional parameter and capital N here in the weights. The weights are not linear, but you have to put this fractional power, capital N over small n. So if you remember the result of Nicolas Juillet saying that in the Heisenberg group you have such an inequality with Bdn equal to 5, automatically proves also the result of Balog. So in some sense, we could get the bridge from this second to the third, and this can be proved simply by having the first so local inequality only for below small radius. But what happens if one computes explicitly the distortion coefficient in the Heisenberg group? What happens if one computes really the limit of the volume of the shrinked ball over the ball? You can prove, you can compute it, that the beta has an explicit expression which is not similar to the one you get in Riemannian geometry. You get a formula which involves a function, which here I denote by S bar of theta, which has this interesting expression. And it is interesting to notice that if you do a Taylor expansion with respect to theta, in theta equal to 0, you see that it behaves like theta to the power 5, because here you get a linear term, the sinus theta give you another linear term, and here, by calculus 1 computation, you see that the term in the bracket is of order theta to power 3. So it is interesting. You get again the 5, because 1 plus 1 plus 3. Oh, I'm sorry. And it is interesting to observe that the beta is again the ratio between the function evaluated in t theta over the function evaluated in theta. So you see again the ratio of something at time t over something at time 1. The second important observation is that the beta is not evaluated in the distance, but it is evaluated on the parameter A, which was, say, involved in how much this helix is going up. Okay, it corresponds geometrically to a vertical part of the initial condition defining the geodesic, which is here a covector because you think in Hamiltonian term. So before going to the last part and explaining our novel approach, I want to make a bridge with control theory. So I will also take advantage of asking if there is any question, because since I don't see any face, maybe if I don't hear any question, I will just go on. And okay, so what is the link with control theory? So you can think that this distortion coefficient, so this limit of ratio between ball shrink to a point over the ball, you can do it not only for this geometric, say, situation, Riemannian or non-Riemannian, but also for other situations, like for instance this one, where you have a variational problem in Rn, where you have a dynamical system here, and you minimize the cost, which is quadratic here, over the trajectories satisfying this dynamical system, where you act as a control. So these are called the linear quadratic problem, because you have a linear dynamic and a quadratic cost to minimize. So the idea is that one could think to use optimal trajectories of this problem, which can be described through an Hamiltonian system, to compute again the ratio that you have here. So you contract a ball to a point through solutions of the system over the volume of the ball. It is interesting to notice that this quantity, in this case, does not depend on the point. So the quantity you have in the left-hand side here is actually independent on the point and can be computed again as some function evaluated at t over a function evaluated at 1. What it is, this function? It is the determinant of the matrix n of t, which arises as a solution of this matrix differential equation, 2n first order system. So first order system with 2n variables. To understand better where it comes from, let's see one example. The simplest example. You take an harmonic oscillator in Rn. It means that you have a free dynamic, so u is the control parameterized the velocity, and so you want to minimize what? The kinetic energy, so here x dot power 2, minus the kinetic force, right? There. And so this integral, when you want to minimize, what you see is that in the previous construction you have big A equal to 0 because there is no drift. Capital B is equal to 1. So remember, I'm going back. You have AX plus BU. So if you want x dot equal to U, A is 0 and B is the identity. And the matrix Q, which was involved in the cost, is just a multiple of the identity. If you plug all this information in the system, so B equal to 1, A equal to 0, you see, interestingly, that you get a Jacobi field equation here when the curvature is equal to K. So the beta in this case is just the Riemannian distortion coefficient of a Riemannian space with constant curvature K. You can similarly produce an example of dynamical system, which is a sort of 1D control of the acceleration, in which you choose suitably the matrix A and B and the potential in order to recover the coefficient of the Heisenberg group. So you can see that this way, this viewpoint from the control of building the beta permits to recover also this, say, strange coefficient, which is not included in the Riemannian theory. Good. So, okay, more in general, in say, the Sub-Riemannian context, we were able, I will skip this because it's a bit technical, but we were able to produce a theorem essentially saying that if along a trajectory you have a bound on the curvature, then you can bound the Sub-Riemannian beta between x and y by some model beta defined on one of these examples. Okay, so the idea is that if you are on a Sub-Riemannian manifold and you have a 2-point x and y, you look to the trajectory, you can build matrices A, B, and Q, like in the previous example of the Heisenberg group, such that the beta T, X, Y, you can compare it with a model beta, which now comes from this class. Okay. Okay, now in the last part, I will tell you something about our new approach, which is, of course, motivated by all the things I have said up to now. Is there any question at this point? Maybe it's, again, a good point.
I have some questions, but maybe at the end of the talk, I will tell you.
Sure. So now remember a bit the issue we have encountered when looking to this limit example, the Heisenberg group. We have seen that we can compute the distortion coefficient beta, but it is not on the Riemannian form. And moreover, it does not depend on the distance, but another function of the geometry. So the idea is to allow to be more flexible when building the theory. So what we say, the starting idea is that the beta should be more general if you want to include the sub-Riemannian case inside the theory. So we say that the beta is not necessarily of the specific form in the Riemannian setting, sinus of something over. It is more in general a function evaluated in t theta over a function evaluated in theta, where the function, denoted here again by S bar, should have a finite order Taylor expansion at 0. So you see that it has order capital D. Then we say that the metric measure space, so metric space with a measure, has also a second object, which is a gauge, another function, which should somehow include the idea, as we were saying here in the second line, that the comparison does not contain as an argument theta, the distance, but some other function of the geometry. So, given, depending on the example, we want that a condition that we will define CD beta n implies that our beta will be bounded by a model beta evaluated in this gauge function. This is the background idea. So, where can I choose this S? Okay, S can be general, actually continues satisfying this condition, but you can think to enlarge the space of, say, choice of S, but not to pick any random one, to take every solution of a matrix Clear-Cut equation with constant matrices A and B. Okay, actually in this case, if you give me A, B, and Q constant, you can compute capital D explicitly. Okay, so there is a specific class which I call Riccati distortion S. Okay, so you can be very general, but you can think to this class, which is generalizing the Riemannian case, which, remember, comes out when you choose A equals 0, B equal to the identity, and Q diagonal constant. You get all the remaining. What is the gauge? The gauge in our theory can be any measurable function, but the theory is more simple when the gauge is continuous. And actually, the natural gauge, it is in the Heisenberg group, it is not continuous at the origin. What is the natural gauge in the Heisenberg group? It is the parameter A that we were defining. And you can see it is not continuous at the origin. So that's why we were allowing G to be measurable. Which makes a bit more complicated the theory, but an important point for some result is, of course, that the new object G is well adapted to the metric D, and so we have a compatibility condition, which we call the MIC condition, which is saying that if you move around a geodesic for the distance D, then the gauge G from gamma 0 gamma t is t times G gamma 0 gamma 1. So G along geodesic should have a behavior which is similar to the distance, okay? Because the distance along a geodesic from gamma 0 to gamma t is t times the distance from a gamma 0 gamma 1. So we want the gauge to have this similar property. I will first say some abstract result and then also some more, say, sub-Riemannian one. Abstract result generalize the result you have in the theory of metric spaces. For instance, if you have your metric space XDM with a gauge G satisfying the condition CD beta n, which I did not write explicitly, but if you have questions at the end of the talk, I can show you the say more formal definition. And if you assume that the beta with respect to the parameter theta is non-decreasing, this includes a sort of a positive curvature condition, then you can prove a so-called doubling property for the measure. So if you are in a space which has bounded curvature in this new sense, and it has positive curvature in the sense that the beta is non-decreasing in theta, then you can prove a global doubling property. Of course, you can also write a conclusion for a local doubling if you are interested, but I'm writing the simplest statement. So again, in Riemann geometry, this assumption means exactly K positive. So you get back to the original statement. Another interesting thing is that if you have that your space satisfy the condition CD beta n, then the capital D, which was, remember, the power you get there, is bound on the Hausdorff dimension of the space. Actually, the support of the measure, but if you think to a measure that is absolutely continuous, for instance, smooth, it is the dimension of the space, okay? Depending if you like more smooth spaces or geometric measure theory here. Okay, then you have a Bishop-Gromov theory also, which concerns set where, okay, the Bishop-Gromov theory is a comparison for the volume of balls, the classical one. Here you have to modify it a little bit, and you have to consider the space of points where not only the distance is less or equal than r, so inside the ball, but also when the gauge is small. And you get back exactly the set we were looking in the previous picture. So you are inside the ball, but you also want that the parameter A is small in the Heisenberg group. So it is this green zone, this VGX0R. It's a sort of volume function centered at x0 with radius r, but also related with the gauge. So if you set gauge ball and gauge spheres as follows, so you see, you fix some rho, for instance, I don't know, you can fix rho equal to 1. You can set the volume is when the gauge is smaller or equal than r, and the sphere, which is a sort of the derivative of the volume, you see. Then if you have a metric measure space with a gauge which is compatible with the distance and satisfy the curvature condition, you get back the statement of Bishop-Gromov that those two functions are monotonally increasing. So these two statements in the Riemannian case recover the classical Bishop-Gromov theory. The two functions are monotonally increasing. Okay, some concrete result with concrete, which is okay, depending how much you think these are concrete. What happens in a true Riemannian manifold? That you have the possibility to fix some natural, say, gauge. And if you think, as in our first example, the Heisenberg group, you remember that we had a vector field which was killed when epsilon was going to 0. So you can think that if epsilon is 1, you have a Riemannian extension which is equal to the metric on the first vector field. So you can use this Riemannian extension to define a Riemannian gradient of the distance. And actually in the Heisenberg group, the value A can be defined this way. The square root of this Riemannian, say, gradient of a Riemannian distance square minus the distance square itself. It's a sort of complement of the horizontal distance. And more in general, you can say that any natural gauge function is a gauge which is a function of small d and big D, and which is one homogeneous, okay, in this sense. Okay, so if you have some subriemannian manifold satisfying a strong bracket generating assumption, and if you choose as a gauge this say vertical Riemannian gradient, you can prove essentially that any compact subriemannian manifold, you can find a beta from the class of the Riccati distortion that satisfies the CD, beta, and condition. So you can think to this theorem as analog of the theorem saying that a compact Riemannian manifold has curvature bounded from below, right? Because it's compact. So we wanted to check that the theory was consistent in the sense that if you take a compact subriemannian manifold, there exists a class in which we can put our manifold. And this is true at least under this assumption that I called here F. So we need some assumption on the structure of the Lie bracket. And another, say, concrete example, which you can think, maybe you have met this example, is the Grushin plane, which is a subriemannian structure on R2, which is the other main example, different than the Heisenberg group, which you are in R2 and you have these two vector fields, dx and xdy. So you see that here the situation is different because you don't have two vector fields which recover a third direction by the Lie bracket, but you have one vector field which is always never vanishing, x1, and the other one which vanish on a line. But still you can produce a subriemannian structure. This is the geometric picture when you look to geodesic in this space. So if you start from a point where x is non-zero, you have your geodesic flow, which still crosses the vertical axis where the second vector field is 0, so all trajectories should cross this line horizontally along the first vector field. And here you get the geodesics from the origin. And what is interesting is that you can do some computation. Here I am just showing you some formulas, but what is the interesting point is that you can see that this Grushin space is actually a quotient of the Heisenberg group, and this suggests the idea that as a quotient the curvature should be bigger, and so you should be able to prove that this space satisfies some curvature conditions since the Heisenberg satisfies. And it is true. You can prove that the Grushin plane satisfies this condition with the same beta of the Heisenberg and with the parameter equal to 2. So to conclude, I did not go into these details, but let me say that you can also define a notion of convergence for metric spaces and how it goes, and get some stability and compactness result. So you can also reproduce that part of the theory, and so we obtain a certain number of results, including this new class. So, for instance, the interesting part is that when you have this initial family of Riemannian metric, which converge to the Heisenberg group, in the Riemannian world, you cannot see them inside a single class, but with our new definition, you can produce this new class where you see all the sequence converging to the limit. Okay, so there are also other results connected to this, but I think I've said many things, so I can stop here and take the rest of time maybe to answer to your question and explain more in detail other points. Thank you.
Thank you, Professor Barilari. A nice talk. We have time for questions. If you have a question, you can write it in the chat or raise your hand to allow you to unmute yourself. Maybe I can start with some questions. In the first theory you present, when you say ideal sub-Riemannian manifold, that hypothesis, maybe I want to know, maybe just like
This one.
yes.
Thank you.
Conditions.
I skipped this point because it's, I mean, it means that so in the terminology used in this setting, it means that all length minimizers come from the Hamiltonian equation, okay? That smooth Hamiltonian equation, because you can think to the problem, to the geodesic problem, as a problem of minimizing a length over a class of curves, right? The class of curves now, in this sub-Riemannian case, is not any curve like in Riemannian geometry, but we have the constraint to be tangent to the vector field. So this produces, you can think to the manifold representing the allowed curves where I want to minimize as a manifold with some singularity. Okay, and the point is that ideal means that the minimizer are not those singular points. Okay, it is a generic assumption which is, for instance, always satisfied when you produce a sub-Riemannian manifold on a contact manifold, like the Heisenberg group. So it is very often satisfied, but to prove our theory, we need this assumption.
Oh, okay, Professor. And another question, maybe if you can go to page 23.
Sure.
I think it's amazing that connection with the control theory. 23, let me see. Okay, I think it's not 23, maybe 24.
Yes.
Yeah, but okay, there. So that theory, you say that there exists if there exists a Q, then you have that inequality for the distortion coefficient. But I want to know if the A and B can be constructed in this theorem, if you know how to.
Yes. Thank you.
Okay.
Thank you. Very nice question, because I did not went into the details. It is interesting that along the curve you are interested. So you have point X and Y, and you take the trajectory. Along this trajectory, you can compute explicitly some Lie bracket, essentially Lie bracket of your horizontal vector field in the Heisenberg group, say x1, x2, with the vector field given by the direction of the geodesic. Thanks to this, you can compute dimension of certain spaces, okay? Essentially, how many new direction you are producing by taking Lie brackets. And this will build you automatically two matrices, A and B, which essentially have this structure here. You have some, B will be a certain number of 1 on the diagonal, which is exactly the number of the allowed direction. You see you have 2 allowed direction, you have 2, 1. And the matrix A has a certain number of 1 below the main diagonal. The A and B are very explicit, and you can, if you give me an example, I can give you A and B. So all the assumption is in the existence of Q.
Okay, nice. Thank you. And one more question, if you allow me. Maybe
Sure.
this is not so good question, but I wanted to know, maybe if in order to compute that distortion coefficients explicitly, for example, you have the Heisenberg group case, but maybe you can try to set a context, for example, of homogeneous space, consider some symmetries or some conditions on the manifold in order to have explicit formulas for the or explicit computation for the
Yes.
distortion
So
coefficients. Is that true, or?
you're right. There are some examples, in particular symmetric spaces, where you have some symmetry, where you can compute this distortion coefficient. Essentially, this is possible whenever you have some knowledge on the Jacobi field equation, some explicit knowledge. This is also in the Riemannian case, it is not easy, because in the Riemannian case, if you remove the constant curvature case, then to solve the Jacobi field equation explicitly, it is difficult in general. So here you encounter essentially the same problem. But there is quite a good class of examples, say, where you can have some explicit formula.
No, okay,
Not that many, but
a few, right? Okay, Professor. No, thank you. I think this was an amazing talk. Maybe it's very related with some works in Lie theory and control theory from Brazil and Chile. So thank you for giving that nice talk. And
thank you.
okay.
I hope this was of your interest, and I was putting the references at the beginning. So maybe I just show again by saying thank you. You can find more details in this long paper appearing in Memoirs of the American Mathematical Society, and also the previous works.
Thank you. Thank you. Okay, we're moving forward now for our next talk. Let's say thank you to Professor Barilari.
Thank you, everybody.
Just give me a minute, please. Professor Savadini, are you?
Yes, I'm here.
Okay.
Hello. Hi, Davide. Hello. Thank you for your very nice talk.
Thank you. Thank you for being here.
Okay, Professor Savadini, maybe you can try to share your screen.
Yes, of course.
We're going to wait a few minutes,
Sure.
but we can check now if everything is okay.
Let me try to put it full screen.
Okay, we're seeing your screen. Maybe you can try to change the slide.
Yes, 1 second. I'm trying to let this part disappear. Let's see if I can. Actually, I don't know. Okay. It seems that it is good, it can move, so I'm good.
Everything is okay. Okay,
Yes,
just give me 3 more minutes.
sure.
And at 9 o'clock, okay?
Hello, Professor Sabadini.
Yes,
I'm Yuriko Pitones. I am going to do your introduction.
thank
Nice to
you.
meet you.
Nice meeting you.
Are you ready?
Yes, indeed.
Okay. I think it's time I want to start with your introduction. Hello, everyone. It's a pleasure for me to introduce Professor Irene Sabadini. She is an Italian mathematician known for her work in complex analysis and the study of special types of mathematical function. She is professor at the Politecnico di Milano and has focused her research on areas like hyperbolic function, quaternionic function, which are used in advanced mathematics and physics. Professor Sabadini has also written several books and research papers, making important contribution to her field. She is recognized for her expertise in applied mathematics. In this occasion, she talked about quaternionic linear operators as a spectrum and notion of trace. Please.
Thank you very, very much for the introduction. Can you still hear to me? Do you hear me?
I can hear.
Yeah.
Perfect, thank you. So, as the title says, I will treat the topic of quaternionic linear operators and basically what type of notions one can give. And we shall see that the appropriate notion of spectrum to be used in this case is the notion of S spectrum that I will introduce later. What I am presenting is a joint work with Paula Cerejeiras, Fabrizio Colombo, Alberto De Bernardi Pinos, and Uwe Keller. And it has been a quite long work because there are really some delicate points that I hope I can illustrate during this talk. But first of all, let me quickly explain why one should be interested in studying quaternionic matrices or quaternionic linear operators. Of course, one may always argue there is a mathematical interest in any generalization, yes, but in particular, quaternionic matrices are rather used in several fields like robotics, computer vision, just to mention a couple of them, anywhere where rotations, for example, are useful, and also in physics, specifically quantum mechanics, that is known, it is possible to be constructed also over the quaternions. This is known since the 30s of the past century, when a celebrated paper by Birkhoff and von Neumann proved that it is possible to construct quantum mechanics also over the quaternions. Not only that, it is possible to use quaternions to represent some types of vectorial operators. And so it is possible to use tools in quaternionic analysis to deal with them. I will start from scratch because I am assuming not everybody is familiar with quaternions and the algebra of quaternions, so I will start really from the very beginning. What is a quaternion? Well, it is a hypercomplex number generalizing a complex number. A complex number should be of this form. Here we have two extra imaginary units, j and k. Q0, Q1, Q2, Q3 are real numbers, and the imaginary units are such that they have square equal -1. This is somewhat expected. And they anti-commute, so ij equals -ji. And from these relations, you can obtain all the possible relations among the imaginary units. If you look just at the 4 real numbers representing a quaternion, you can get a model of the quaternions as a vector space. The model is R4. As such, you know how to perform the sum. But of course, in order to perform the product, you need to use these rules of multiplication in the algebra. The algebra is associative. This helps. But the product is non-commutative, and it is clearly visible here. And so in general, if you multiply two quaternions, the product PQ is not equal to Q times P. For any quaternion Q as here, you can form the conjugate by simply putting the minus in front of the imaginary units. Any non-zero quaternion admits an inverse. So it's a skew field, basically. And the modulus of a quaternion is defined to be the square root of the, basically, Euclidean type norm. So far, it's really a direct generalization of the complex numbers, bearing in mind that it is non-commutative. As for the complex numbers, given a quaternion, we have a real part, which is Q0, also called the scalar part. And this part, this one here, is called the imaginary or vectorial part of a quaternion, also denoted later in this way. Note, I mentioned at the beginning, that quaternionic multiplication can be used to represent rotations in R3. And when you consider a quaternion Q and any other quaternion S non-zero, then the new quaternion S inverse times Q times S as a rotated imaginary part with respect to Q. And this is very efficient because if you represent a rotation using a matrix, then you have to deal with the product of matrices, which is computationally expensive. Using the rules of the algebra of quaternions, the calculations are easier and less expensive from the computational point of view. Now, let me show you that you can write any quaternion like if it is a complex number. What I mean is that consider the vectorial part and assume that it is non-zero. So basically, this is like to say that the quaternion lambda is not real. So it has an imaginary part, non-zero. Then take this imaginary part, divide it by its modulus, and what you get is an element that I denoted here by capital I. And basically, lambda, the quaternion, can be rewritten as lambda naught plus I, this I here, times some other real number that I denote by lambda v. Note that the set of elements which are purely vectorial and with modulus equal 1 contains elements whose square is -1. So we have an entire sphere. It's a two-dimensional sphere in R3. R3 is a model for the vectorial part of a quaternion. So you have a two-dimensional sphere in a three-dimensional space. You have an infinite number of imaginary units. So basically, if you look at lambda written in this way, it's in practice written in a complex form. Although this capital I is a quaternion, so when you take another imaginary unit in S, it does not commute with I. As we shall see, well, I will not discuss that in detail, but if you consider the set of elements of the form lambda 0 plus j lambda v with j in the sphere S, what you get is an equivalence class. So the set of these elements is an equivalence class. It is the class of the other quaternions of the form lambda prime, namely the quaternions of the form S inverse times lambda times S. All the quaternions with rotated vectorial part. One can prove that this is an equivalence class, and I will denote it by lambda. It's a two-dimensional sphere in the set of quaternions. Now I will move to quaternionic matrices. If we consider any finite dimensional vector space over H, by fixing a basis, this vector space becomes H to the power n. I didn't say at the beginning, but I denoted the space of quaternions by the letter H in honor of Hamilton, who introduced quaternions in the year 1843. So quaternions have a birth date, which is 1843. Now let us consider linear maps between Hn to itself. What you get is a matrix, square matrix, n times n, with quaternionic entries. Now, given a matrix, you may ask yourself, what is an eigenvalue? Well, first of all, being the ambient non-commutative, first of all, we have to decide if we are considering a linear space on the left or on the right. The two descriptions are fully equivalent, of course different, but equivalent, but we have to make a choice. Traditionally, one considers vector spaces on the right. So let us consider right linear maps between Hn to itself. We consider a matrix A. An eigenvalue lambda of this matrix, a right eigenvalue, is a quaternion lambda such that there exists a non-zero vector x satisfying this relation here. Well, rather natural. But note that whenever you have an eigenvalue lambda, in reality, you have an entire equivalence class of eigenvalues. Indeed, any element of the form lambda prime equal S inverse times lambda times S is still an eigenvalue of A. How can we see that? Well, we know that X satisfies, by assumption, this relation. Now, multiply by S the vector X. Then you use associativity here. Then you know that X is an eigenvector. So you rewrite X lambda times S. And then if you multiply here by S inverse, in practice you are doing nothing, it's a neutral operation here, you get that XS is now an eigenvector, but related to the eigenvalue lambda prime. And this shows my claim. Whenever you have an eigenvalue, you have an infinite number of eigenvalues, all of them in the same equivalence class. What do lambda and lambda prime have in common? Well, if you think on how they are written, they are both of the form lambda 0 plus some imaginary unit times lambda v. Well, they both satisfy the relations real part of lambda equal real part of lambda prime, and they have the same modulus. So these two quantities, the real part and the modulus, or the modulus of the vector part, which is equivalent, fully characterize the equivalence class. Another information, which is not good news, if you consider the operator A minus the identity matrix times lambda on the right, this operator is not right linear. If you redo the calculations we already did a moment ago, well, you see that there is no way to have S written on the right. It is simply not possible because we are working in a non-commutative setting. Moreover, X times S is an eigenvalue associated with a different eigenvalue, lambda prime, not anymore lambda. So basically, the eigenspaces are ill-defined. There cannot be the notion of eigenspace associated with lambda, because you clearly see that the set is not closed under the multiplication by a scalar on the right. And this is a problem. So in my title, I was mentioning the notions of trace. Now, how can we define the trace of a matrix and to expect that this is equal to the sum of all eigenvalues? Just when you have one eigenvalue, you have an infinite number of eigenvalues. So this cannot be possible. So how to do that? A similar question. We know that the determinant is also classically, in the complex case, related to the eigenvalues. It is the product of the eigenvalues. Here, well, there cannot be such a notion. Even more, what is a good notion of determinant here? Think about the simplest case, a 2 by 2 matrix. Well, when you take the product on the main diagonal and on the secondary diagonal, how to take the product, in which order? If you change the order, by definition, you get a different value for the determinant. And if you take larger and larger matrices, the problem becomes even more complicated. So how to have a good notion of determinant and to relate it with the notion of eigenvalues? Even more in general, can we construct a characteristic polynomial which is related with the entries of the matrix and also to the eigenvalues? And then, how to deal with the problem of eigenspaces? Eigenspaces are ill-defined, so how to handle eigenspaces? Okay, let me start with the case of matrices. First of all, let us fix one of the imaginary units. We have an infinite number of imaginary units. We have an entire sphere. Let us fix one imaginary unit. So if we choose the basis of the quaternions given by I, j, and k, let us fix I. So when I write C, I mean the complex plane associated with the imaginary unit I. This is a choice, an arbitrary choice. With this choice, a quaternion Q can be written as a complex number Z1, which is Q0 plus IQ1, plus another complex number Z2 times J. And Z1, Z2 are complex numbers. Similarly, we can decompose our matrix A as a sum of a matrix A1 with entries in C plus A2 with entries in C times J. And these are two matrices with complex entries. It's very classical to associate with the matrix A another matrix chi sub A, which of course depends on this choice, which is constructed in this way. Later on, for simplicity, I will call this matrix simply chi, not chi of A. This matrix captures the non-commutative nature of the original quaternionic matrix A. This is very well known since the middle of the past century. And the companion matrix also solves the problems of working directly with the quaternionic matrices. We have a theorem, which is very well known. When you have a quaternionic matrix, then a complex number is an eigenvalue of the original quaternionic matrix A, if and only if both lambda and lambda bar, the conjugate, are eigenvalues of the matrix chi. So basically what I'm saying is that there are equivalence classes of eigenvalues, right eigenvalues, but we can pick in each equivalence class an element, let's say lambda, which is inside this complex plane. Let us pick the lambda with positive imaginary part, and then automatically we have the rotated eigenvalue on the same complex plane, which is lambda bar. And as I said, in each equivalence class of a certain eigenvalue, we have two eigenvalues that are the eigenvalues of the companion matrix. These are called standard eigenvalues, and standard eigenvalues are those ones with positive imaginary part. So, having the companion matrix, we can associate to this matrix the standard invariant quantities. In particular, what would be the trace? Well, we can define a trace that I denote here by TH1 to the matrix A, which is going to be, by definition, the trace of chi. Now, look at the trace of chi. This is a complex matrix. You have the diagonal elements in A1 and in A1 bar. So basically, it is like to take twice the real part of the summation of the diagonal elements in A1. And if lambda 1, lambda 2, blah, blah, up to lambda n are the standard eigenvalues of A, then the trace TH1 of A is what? Well, it is the summation of the eigenvalues of chi. They are in pairs, lambda and lambda conjugate. So basically, we have twice the real part of the sum of the standard eigenvalues. And of course, the determinant can be defined to be the determinant of the companion matrix. Again, it is the product of conjugate numbers, and so it is the product of moduli squared. What will be the characteristic polynomial? Okay, this can be discussed. Now, here I put, by definition, that it is the determinant. Here I wrote in form of Fredon determinant. I mean, already the determinant that could be useful to find the, well, that can be related with eigenvalues, so I minus ZA. Here, by definition, I put the determinant of I, which has double size, minus Z times chi of A. This is a choice. Why? Because I could have taken this quaternionic matrix and I could have put, by definition, that the determinant would have been the determinant of chi of this entire matrix. So chi whose subscript is I minus ZA. This would be a different definition. However, we realized that this definition is not good because, as you will see in a moment, we expect this function to be an entire function in the variable z. If you consider chi of this matrix, you automatically have z bar appearing in the discussion, which is not what we want later on. So definitely after this discussion, I can set by definition the determinant of I minus ZA over the quaternions to be this determinant. And of course, working on the complex numbers, it is equal to this quantity. But we also know from the complex case that the determinant can be written as a polynomial of degree 2n, because 2n is the size of the matrix chi. And here the coefficients, apart from the sign, are the traces of the exterior product of chi. So basically, this quantity here can be computed as 1 over k factorial times this determinant, and this is a complex determinant. Now, since by definition we said, let me go back, that this one is TH1, I can write in place of this TH1, and then I can also set by definition that this is THK, just by definition. And of course, now that I have this definition, I can also change the notation here and write in this way. So at the moment, to recap, I have written this determinant as a polynomial whose coefficients are some higher order traces. The first order trace, TH1, satisfies, because of the matrix chi, this relation. However, we know that we don't have at quaternionic level just one eigenvalue. When we have one eigenvalue, we have an equivalence class, and the real part of an eigenvalue does not describe at all the equivalence class. We also need a quantity describing the modulus of the eigenvalue. So for sure, just one trace is not enough to gain information on the eigenvalues. The information is found in the second order trace. The second order trace, TH2, by definition is this quantity. It is this determinant divided by 2. Now here I have written equal, but in reality it's a theorem or a proposition, I mean something that you need to prove. These are just bloody calculations, but if you perform the calculations, you discover that the second order trace equals the sum of the moduli square of the n representative of the n eigenclasses plus a quantity which takes into account again the real part. Yes, but we need a quantity that can be related directly with the entries of a matrix. Why? Because normally you don't know in advance, a priori, the eigenvalues. You just have in front of you a matrix and you want to recover the values of the traces simply looking at the entries of the matrix, not computing the eigenvalues. Well, it is possible to show that the second order trace, in fact, equals this expression here, and so it can be computed directly from the matrix without computing the eigenvalues. The quaternionic Fredholm determinant, which is this quantity that I defined a moment ago in terms of the determinant of the chi matrix, satisfies this identity. Now, when we proved this identity, we realized that we were on a good track. Note that this Fredholm determinant is a product of second-order polynomials of this form. Note that the only information needed here is the real part of an eigenvalue, and this is a characteristic of the equivalence class, and the modulus square of the eigenvalue, any of the eigenvalues in the equivalence class. And this also has a shape which reminded us the S spectrum. So we realized that we were on a good track. Now, just to provide an example, take the simplest case on Earth, a 2x2 matrix. Even simpler, a diagonal matrix. Now, I put on the diagonal 3 plus I, and basically this is K, the product IJ. But I wrote IJ because in this way, you immediately see what is the matrix A1 and what is A2. So the standard eigenvalues are 3 plus I, which is the only non-zero element in A1, and I, which is the only non-zero element in A2. The characteristic polynomial can be computed, and it is this polynomial here. But look, the linear term has coefficient which is -2, the real part of the sum of the elements on the diagonal, which is exactly -6. So basically it is the opposite of the first order trace. While the quadratic term has coefficient 11, which is exactly this quantity expressed before. And if you go over with 6 and 10, you discover that these are the third order and fourth order trace. Namely, fourth order means the determinant. So, in summary, the fact that eigenvalues are equivalence classes of elements explain the need of more information to be encoded in the notion of trace. So just one trace is not enough. Then, for matrices, we may refer to the companion matrix. But if we speak about linear operators, what to do? We don't have the way out of using a complex trig. Moreover, what happens if the spectrum is not reduced to the point spectrum? Namely, what happens when we don't have only eigenvalues? What to do? Well, the answer is, for quaternionic linear operators, the appropriate notion of spectrum is the so-called S-spectrum that was introduced by Fabrizio Colombo and myself in 2006. What is the S-spectrum? Now, the definition that I'm using here is this one. The definition is given for an operator, let's say A, acting on a Banach space that I denote here by V. V is a quaternionic right linear space. And by calligraphic B of V, I am denoting the set of bounded right linear operators acting on V. The S spectrum is defined to be the set of quaternions lambda such that A squared minus twice the real part of lambda times A plus modulus square of lambda times the identity operator is not invertible as bounded operator. The S-resolvent set is the complement of the spectrum. So basically, the notion of spectrum is not given in terms of the invertibility of the operator A minus lambda times I or I times lambda, but it is in terms of a second order operator. Note that the S spectrum is actually symmetric, namely, whenever you have an element lambda 0 of this form in the spectrum, then by changing J and taking in place of J any other I in the sphere, then you still have an element in the spectrum. In other words, the equivalence class of lambda 0 is contained in the spectrum. The point S spectrum, which is the set of eigenvalues, is what? Well, as in the classical case, it is the set of quaternions such that the kernel of this second order operator is non-trivial. And what is very good is that the point S spectrum coincides with the set of right eigenvalues. It is also true, just to let you know, that the S spectrum is a compact, non-empty set in the set of quaternions. The second order operator, which corresponds to the inverse when lambda is in the resolvent, is called the pseudo S resolvent. And it is important to note that it is this operator here, a quaternionic right linear operator, and in practice it is the linear operator associated with the right eigenvalue problem, which is not linear. We discussed that before. So normally what you do in the complex case is to study the invertibility of this linear operator. But since this is not a linear operator, this has no meaning over the quaternions. The operator that we want to invert is this one. What is an eigenvector? It's a non-zero vector which solves this second order equation. And note that here, the information contained in this equation is the real part of lambda and the modulus squared. So basically you can say that V is an eigenvector related with the equivalence class, not with just one eigenvector. And this also solves the problem of the eigenspaces. Now, having this in mind, how to use this information in order to proceed and to define in a good way a notion of trace, for example, in a Hilbert space. So we know that in a finite dimensional space, if you have a linear map means right linear, it can be expressed by fixing an orthonormal basis via a matrix in this way, where once that you fix this basis, X prime is the dual basis. Namely, it is obtained by the original basis by applying on the left the adjoint matrix. So what we want is to extend this to the case of infinite dimensional spaces, so basically infinite size matrices. Now, the first step is that we proved that for finite rank operators, we can define a notion of trace in this way. Basically, you go back to the finite dimensional case. This is consistent also with the calculations of the power of the operator T. I'll skip this because I don't want to discuss more. But basically, you can introduce the first order trace, the second order trace, as we did before, and also a notion of Fredol determinant. This for finite rank operators. But if you move to the general case, this is where I wanted to go, you can consider a right linear operator T from a Hilbert space H to itself. Of course, we assume that it is separable. And in our discussion, we also assume that the operator is of trace class. Namely, when you take the sum of the moduli of the diagonal elements, namely this one, and this is a series because you have an infinite matrix, the sum is finite. Here I denoted by xk into bracket an orthonormal basis of the Hilbert space H. Now, this allows, in the classical complex case, now I'm in the classical case, to define the trace in this way. Basically, it is the series of the diagonal elements. The Fredol determinant is defined in this way via the traces of the exterior products of T, like we did before. Always in the classical case, can we relate this notion of trace and Fredol determinant with the eigenvalues? Answer is yes, and this is the content of the so-called Grothendieck-Lidsky formula. So in the classical complex case, if you have a Hilbert separable space and an operator T which is trace class, assume to have the sequence of eigenvalues, then you have that the trace is going to be the series, which is convergent, of the eigenvalues, and the Fredholm determinant can be expressed in this form. Note, although this is not relevant in our discussion, but on the side, as a function of z, this is an entire function. Moreover, it is an entire function of order 1 and genus 0. Basically, the order can be computed via, let me say, the coefficients of the series expansion of the entire function, and the genus can be obtained via this expression. But again, this is not relevant for this discussion. So how to do this in the quaternionic case? If we consider a quaternionic Hilbert space separable, we assume to consider T right linear operator Fixing a basis, xk, we have the dual basis, and we can form this representative matrix of the linear operator. Let me still denote the matrix by the letter T. We know that for the matrices we have, and also for finite rank operator, we have these two relations. And these relations for the matrices, of course, do not depend on the choice of the basis. But what about our case? Remember that we had problems in the definition of eigenspaces and so on, so this is a sensitive problem. Well, what we proved is the quaternionic analog of the Grothendieck-Lidsky formula. How can the statement be formulated? Assume to consider a trace class operator on a quaternionic Hilbert space. Assume to consider the sequence of standard eigenvalues, namely, you have always equivalence classes. Yes. Choose a complex plane and pick the representative in each equivalence class, which belongs to the upper half complex plane. Then we have that the trace TH1 is given by twice the sum of this series. The second order trace, I put here some dots, is expressed exactly by the same expression given by the matrices. And the Fredholm determinant is expressed exactly by the product of elements as we did for matrices. Of course, here we have an infinite product. Note that the Fredholm determinant as a function of Z is an entire function of order 1 and genus 0. And here, recall that we didn't want Z and Z bar, and so we have chosen to apply, well, we have chosen the chi of the matrix or of the operator, not of the entire operator I minus lambda t. Note also that here I put standard eigenvalues because here I must specify what are the lambda that I am writing. But in fact, we are taking the real part. So this is completely not sensitive to the choice of the representative, and not even this expression is sensitive to the choice of the representative in the equivalence class. Can this be pushed further? Yes, we can move to the case of a quaternionic Banach space. Let me denote it by X. For some types of linear operators. Specifically, we consider operators T, which are nuclear. Namely, they admit a representation of this form where I fixed a basis xk so that we immediately get the dual basis xk prime. By this, I mean I multiply xk by the quaternion that I obtain by applying xk prime to the input vector x. Moreover, we assume that this quantity here is finite. Well, the infimum of these quantities is finite. This is denoted by norm R. And when R equals 1, we say that the operator is nuclear. So we don't call it one nuclear, but simply nuclear. Note that when X is in particular a Hilbert space, to say that the operator is nuclear is the same as to say that the operator is trace class. So in principle, I can recycle what I did before. Now, already in the classical complex plane, there is this question. Is it true for nuclear operators that this quantity is well defined? Namely, it is independent of the choice of the basis xk and in consequence of the dual basis? Well, already in the classical case, the answer is it depends. It is true under an additional technical assumption on the Banach space, namely it must satisfy the, well, it is true if it satisfies the approximation property, otherwise, in general, it is false. However, Grothendieck showed that the answer is always positive for 2/3 nuclear operators. So we concentrated directly on 2/3 nuclear operators. And we could prove the analog of the Grothendieck-Lidsky formula in the quaternionic case for a quaternionic Banach space having the approximation property, and we considered a 2/3 nuclear operator. Again, considering the sequence of standard eigenvalues, then we can define the trace TH1, TH2, and they are proven to be equal to these quantities. And as to the Fredholm determinant, we wrote it in the case we choose z equal -1, so we have this expression that still relates the Fredholm determinant to the k-order traces. And note that a crucial step is to show the independence of the choice of the basis. We could prove that. We went even further. Mimicking the classical case, Grothendieck considered the general context of locally convex spaces and their tensor product. Basically, the operators can be represented in this way, and depending on the topological properties of E, the trace may be properly defined, and there is the possibility to have the analog of the Grothendieck-Lidsky formula. We could extend also this discussion to the quaternionic case. It is extremely technical, especially because to define in an appropriate way the tensor product is really something difficult and full of technicalities, but we could do that. And if you are interested, I recommend the source of this talk, which is this recent paper appeared in Advances in Math this year. And I thank you for your attention.
Thank you very much for your nice talk, Professor Irene. Now we have time for a couple of questions. If anyone have questions, please write them in the chat. We have one. The question is there an analog of the concept of holomorphic function in the quaternion setting?
Thank you for the question. It's a very interesting one. There is a notion, well, there are various notions. One was given in the 30s of the past century by Moisil and Feuchter independently. Then Feuchter and his school worked intensively on this class of functions. These are holomorphic functions which are defined to be, let's say, smooth functions in the kernel of a Cauchy-Riemann type operator, which instead of having just one imaginary unit, it has two extra imaginary units and two extra variables. So basically, derivative with respect to the real part plus I derivative with respect to, let's say, Q1 plus J derivative with respect to Q2 plus K derivative with respect to K3. And this is one notion. It is good, very good from several points of view. Basically, you can obtain all the results you expect in the classical theory of holomorphic functions, with some exceptions and with a lot of care. Because, for example, it is not true that if you take a quaternion to some power, so the monomial, the simplest one, q to the power n, even less, just q, this is not in the class of holomorphic functions. Then there were other attempts, another one more recent, which goes back to the year 2006, was given by Gentili and Struppa, who elaborated an idea of Cullen of the 50s, I think, that is to see the quaternionic space as the union of complex spaces, and then you can impose that the restriction of a function to each of these complex spaces is in the kernel of the corresponding Cauchy-Riemann operator. You obtain another notion of holomorphicity, which this time includes powers. So q to the power n is included in the class of holomorphic functions in this sense. There are other possibilities to define holomorphicity, but I should say that those two are the most successful. Namely, in terms of number of papers and consequences and applications.
Okay, thank you. Another question or comment?
Maybe I have a question for Professor Sabadini. Can you hear me?
Yes.
Yes. Hi, Professor Sabadini. Thanks for
Hello?
accepting our invitation. Okay, so my question is the following. You show you show this notion of trace for two-tiered nuclear operators, right?
Mm-hmm.
Some results also for LP spaces in the classical setting that allow us to analyze the trace when R, the index of nuclearity, belongs to the interval between two-tiered and one. I wonder, as a curiosity, if had you in the contest analyze if this also can be known, or if it doesn't make sense.
No, actually, we didn't examine this setting. What we did so far is exactly what I presented here. So, well, to be more specific, in the case of locally convex spaces, we concentrated on the case two-third nuclear, but we have some technical results where we consider R in between 0 and two-third as technical results. But our aim, well, in that paper at least, was not to study other cases because this was the first paper on the topic. So I don't know what can be the answer. It can be something for the future. So thank you for the question.
Thank you very much for the very nice talk.
Thank you.
In the chat, Jesus also asked about
the name of the last author.
Yeah, please.
Well, I put just the initials because it's me. So let me go back. So IS stands for Irene Sabadini. And Uwe Keller, and before De Bernardi Pinos, Colombo, and Cerejeiras. Backward.
Thank you. Another question or comment? No. So we thank again the Professor Irene
Thank you
for
very
the
much.
nice talk and for accept the invitation to be here in this conference of ICMAM. Thank you
so much. Thank you very much for the invitation. Thank you.
Thank you. And now the Professor Claudia Gareto is here. Hello. Oh,
Hello, everyone. Can you hear me?
Ciao, Claudia. I wanted to stay online to
Ciao.
say hello. Ciao.
Ciao.
3 Italians in a row, actually 4, because there was Serena Di Piero this morning. So,
Fantastic, fantastic.
ciao, ciao.
Ciao. Okay, so muchas gracias por invitarme. I'm gonna switch to English now. Should I share my screen?
yeah, please.
Okay. Let me see, share screen. Okay, here we go. Let's see if it works. Okay, let me put it like full screen. Where is it? Enter full screen. Yes.
Yeah, it's nice.
Visible? Okay. Let me just maybe we should move this like
For your
the
introduction,
Zoom thing here. Okay. Yes.
the one is here for the introduction for Professor Claudia.
Yes, yes, thank you.
Gracias.
Thank you, Yuriko. Hi, Claudia. How are you?
Hi. Hola.
Thank you for accepting our invitation.
It's my pleasure.
Okay, as usual, then ICMAM Latin America, we say some words about the speaker. Then please, Claudia, let me just give a
Please.
short presentation about it. So, to all the attendees of ICMAM Latin America 2024, I will say that it's my great pleasure to introduce Professor Claudia Gareto, who is an Italian mathematician, a distinguished mathematician, working in partial differential equations and mathematical analysis. Currently, she is professor in the School of Mathematics at Winmer University of London and a visited professor at Loughborough University. Previously, she was a junior research fellow at Imperial College, London. Let me say also that her research focus on advanced topics such as hyperbolic equations and systems with multiplicities, PDEs with singular coefficients and very weak solutions, subelliptic problems on compactly groups and microlocal analysis, Fourier integral operators and pseudo differential operator, as well as algebras of generalized functions. Professor Claudia Gareto got her PhD in mathematics from the University of Torino in 2005 in collaboration with the University of Innsbruck, where she also obtained her habilitation in 2009. She has received awards like the Daiwa Adrian Prize for the UK Japan collaboration and is member of prominent mathematical societies such as the London Mathematical Society, and also she is board member of ISAC, which is the International Society for Analysis, Applications, and Computation. So, Claudia, thank you very much for accepting our invitation, and please continue with your talk titled on higher order hyperbolic equation with multiplicities.
Thank you very much for such a nice introduction, and thank you for inviting me. I really admire the work that you are doing for the Latin American mathematical community. All right, so my talk is, I would say, a survey talk because I thought that maybe it was a good idea not to be too technical. So I will report on some recent results on higher order hyperbolic equations with multiplicities. So, okay, let's see why I cannot move here. Okay. All right, so it seems that I cannot actually move the pages. Okay, let me have a look. Sorry, I just need to adjust this. Okay, here we go. All right, so I will start with some introduction. Then I will mainly focus on the methods that in collaboration with Michael Różański and other mathematicians like Christian Ye and Boris Abitbek, we developed for non-diagonalizable hyperbolic systems, because you will see there is basically a strict link between understanding the system and then understanding higher order hyperbolic equations. And in the last part of the talk, I will show you how we can apply those methods developed for system to study hyperbolic equations of higher order with multiplicities. All right, so let's start with some... I don't know where to put this thing, maybe here. Okay, let's start with a little bit of like the framework so that we all have the same definitions. I'm interested in equations of higher order, so let's say arbitrary order m, and they can be written in this way, where with d, I mean the partial derivative with a minus I in front. So the operators a, m minus j are differential operators of order m minus j. And when I want to denote their principal part, then I will put some parentheses here around the index m minus j. Here I have written a Cauchy problem. So my intention is to study the Cauchy problem and to understand whether it is a C-infinity well posed or not. But as I said before, I'm working with hyperbolic equations. So when do we say that an equation is hyperbolic? So what we do is something that at the first sight can look very formal. So I will take the principal part of these operators, and then I will formally replace dt with tau and dx with xc. And what I get is the so-called characteristic polynomial, which is a polynomial in tau with coefficients depending on t, x, and xc. Now, if I can find m real roots for this polynomial, then I will say that my equation is hyperbolic. So an equation is hyperbolic if the corresponding characteristic polynomial has m real roots. Of course, these roots that I will denote here with tau L will depend on time, space, and xc. So they might coincide somewhere. And when they coincide, we say that this equation has multiplicities. And in some communities, for instance, if you look at the papers written by the hyperbolic community in Italy, for example, years ago, when there are multiplicities, often they call the equation weakly hyperbolic. And they make a distinction between the weakly hyperbolic case and the strictly hyperbolic case, which is the case when the roots never coincide. So at the beginning of my talk, I was saying that actually I'm cheating a little bit. So I told you that I want to study equation, but what I do in reality is immediately transforming the equation into a system, and then I will study a first order hyperbolic system. And the transformation is quite classical, it's quite standard. You can find it in many books. For instance, you can find it in a book by Taylor on pseudo-differential operators. And if you're familiar with pseudo-differential operators, you will see that here we are using one of them. So we are using the one which has the symbol Japanese bracket of c to the power m minus k. So this transformation is done in such a way that I get a system which is of the first order, but also the matrix of the system has a very special form. It is in Sylvestre form, which is exactly the one that you see here. And clearly, I have to perform the transformation everywhere, so not only on the equation, but also on the initial data. And there are precise formulas, so you can write precisely what are the entries of this equation. So even if I start with an equation, right, a partial differential equation, because I'm using pseudo-differential operators, what I have here now is a system of pseudo-differential equations, which has the advantage that clearly I have quite a strong theory behind. I have the theory, the operator theory of pseudo-differential operators. But also, I realized that the size of this matrix is exactly the order of the equation. So I have a matrix which is of size m times n. The size of the space where I work doesn't play a role. And this is quite important, and I would not get this effect if instead of using pseudo-differential operators here, I would use only differential operators. So if now I look at the matrix of the symbols, right? So I pass from operators to symbols, and I am a little bit careful, so I make a distinction between the principal part of the operators and everything else, so what is lower the terms. Then I will have a matrix A of the first order, which is the principal part, which is the one written here, which is clearly in Sylvester form because I have this specific form here. And all the lower order terms will go into a matrix B, which is quite simple because the only row which is not identically 0 is the last one. If I have done my transformation correctly, then I will have that if I compute the eigenvalues of the matrix A, I recover the roots of the original equation. All right, here we go. So let's have an example, because I believe examples will actually help us to fix the ideas and to have an understanding. Probably the easiest and most famous example of an hyperbolic equation is the wave equation. And because I want to consider like variable coefficient, then I'm assuming that I have a variable coefficient A depending on time and space. Right, sorry. Here we go. Again, for the sake of simplicity, let's work in space dimension 1. So the wave equation is written in that form, and I have a Cauchy problem with the initial data G1 and G2. If I now perform the transformation that I showed you earlier, so I pass from the equation to the characteristic polynomial, then I get a characteristic polynomial of the second order, which will have 2 roots. Now you see why you need A to be positive, because you want to find the 2 real roots, and clearly you need to be able to compute this root here. Now, if the coefficient A never vanishes, then we have a strictly hyperbolic equation, so we have no multiplicities. If the coefficient A has some zeros, then in those points we will have multiplicities, and this is the so-called weakly hyperbolic case. So now, what do we know about these hyperbolic Cauchy problems? I mean, a bit of history. Okay, writing as a title of the slide, a bit of history is actually quite ambitious, because the history of the theory of partial differential equation is huge, right? So I will just mention some results which are probably the ones most connected with what I do, and I'm very much aware that I'm probably forgetting many other important and nice results. So please, apologies in advance. All right, so when the roots are distinct and we are in the weakly hyperbolic case, we know almost everything. So what it means that we know that under suitable conditions of regularity, which are actually not too restrictive, the Cauchy problem will be C-infinity well posed. We know that the lower order terms do not really play a role. What really counts, it's only the principal part. But in the case of multiplicities, then it's a completely different picture. So there are still problems that are open. There are still situations that we do not understand fully. There might be results that rely on the dimension of the space. So results that are being proven in space dimension 1 only. There might be results where we have some technical assumptions on the multiplicities. So the picture is completely different, and that's why it is actually interesting for me. So it could happen that in the presence of multiplicities, C-infinity well-posed is not guaranteed. And this was observed already many years ago. So mathematicians realized that, okay, so we might fail to prove C-infinity well-posedness. So they had questions like, where do we prove the well-posedness? But they also realized that in presence of multiplicities, the lower the terms cannot be neglected. They play a relevant role, and you might need conditions on them in order to prove the well-posedness of your Cauchy problem. And these are called the C-infinity Levy conditions, sorry. I am quoting here an important result by Olinek in the 70s. So Olinek wanted to study second-order hyperbolic equations with variable coefficients, and she wanted to provide sufficient conditions in order to prove the C-infinity well-posedness. And in the case of the wave equation that I showed you earlier, this condition, the Olinek condition, can be written in this way. So it is basically a relation between the coefficient A in the wave equation and also the time derivative of A. And it is actually quite easy to check if this condition is fulfilled or not. For instance, if we have a coefficient that depends only on time, then Olinek's condition is easily fulfilled when A is positive and it is also increasing. Her result was actually much more general, right, for a second-order hyperbolic equation in divergent form, but here for the sake of simplicity, I just wrote it down for the wave equation. When Olinek condition is not fulfilled, then we might end up with no C-infinity well-posedness. And bear in mind that we are working only with order 2 equations here, right? So we are not working in generality. So already in the case m equal to 2, we might have cases where the C-infinity well-posedness is not achievable. And this is a very famous result by Colombini and Spagnolo. And again, it's an equation which looks harmless, if you want. So it's a wave equation, space dimension 1, time-dependent coefficient only. They constructed this example they constructed specific coefficient A such that this Cauchy problem does not have a solution in the space of distributions. So, what do we do then? Okay, so if we cannot achieve C-infinity well-posedness, maybe we should look for well-posedness in a different space. And one idea that has been actually quite successful because I brought to the publication of many papers was to choose more regular initial data, which means initial data in Gevrey classes, and then to prove Gevrey well-posedness. And there are actually many results of Gevrey well-posedness for weakly hyperbolic equations. I have contributed to some of them together with Michael, but there are also like authors like Colombini, Kinoshita, Spagnolo, Tagliatella, and many others. Many papers have been written when the coefficients depend on time only, and there are far less results when the coefficients depend on x as well. And this is mainly due to the fact that the methods that are used in the proof are very different, because with time-dependent coefficients, the idea is you transform the equation into a system, you apply the Fourier transform, and you go from there with energy estimates. But when x enters the picture, this method will not work anymore, and you need much more like complicated theories, operator theories like Fourier integral operators and so on. So the level of technical difficulty is much higher. Okay, so finally, I also would like to let you notice that Olinek result has not been extended to higher order equations yet. And we are talking about a result which was proven in the 70s. So since then, we couldn't actually get a similar result valid for general hyperbolic M-order equations. And there have been some studies, but mainly on some specific classes of equations with some assumptions on the multiplicities, maybe multiplicities up to order 2, but they are not actually very general. Okay, so what I would like to do in this talk is to show you some results that I've been obtaining in collaboration with Michael Różański and Christian Ye. Christian was a postdoc of mine at my previous institution, Loughborough University. And then once we understand how these results have been obtained, in the last part of the talk, I will show you how now we can transfer our knowledge on non-diagonalizable system from the system to higher order hyperbolic equations. So this is the kind of system that I want to consider. So I will have now first order systems, right? So this will be a matrix of pseudo-differential operators of order 1. I say an hyperbolic matrix, which means that when I compute the symbol and then I compute the eigenvalues of the matrix A, T, X, C, then I get M real eigenvalues. And then I have a matrix here of lower order terms. And this matrix B will be a matrix of pseudo-differential operators of order 0. Now, in 2013, Todor Gramchev and Michael Różański obtained Sobolev well-posedness of every order, and as a consequence, C-infinity well-posedness for systems of this type when the matrices have size 2. And their result, which was actually quite interesting, started from an observation. So under suitable hypotheses on the eigenvectors, it is possible to transform the matrix A into upper triangular form. And once you have done the transformation into upper triangular form, then you are in a much better position because you can actually solve your system, like you solve the equation at the bottom and then you pass to solve the equation in row 1. And you can solve these equations making use of the theory of Fourier integral operators. So the key of their argument was find the hypothesis on the eigenvectors that will allow you to reduce your system into upper triangular form, and then you can solve the system. To give you an idea, the hypothesis that allows this upper triangularization is an hypothesis on the eigenvector, which looks like the one in the box. So there exists an eigenvector H with a component Hi. I is 1 or 2 in this case, which is always different from 0. Okay, and this is independent of T, X, and C. So when we are under this assumption, then we can have a sort of a generalized sure triangularization, and we can reduce the system into upper triangular form. And that is the key to obtain the Sobolev well-posedness. So clearly, there are some questions here, okay? So is this result only true for matrices of size 2, or can we extend it, right, to any matrix size? And the other question is, do we need special hypotheses on the matrix of the lower order terms B? And to answer this question in a quick way, yes, we can extend, yes, we can extend this result to matrices of any size. And yes, we will need specific hypotheses on the matrix B. And these are for us the so-called Levy condition. It is actually quite expected that we cannot have any matrix B, that we need these Levy conditions, because if you remember what I said at the beginning of my talk, when we have multiplicities, the lower the terms play a relevant role, and somehow they need to be connected to the principal part of your equation, or in this case, the system. So we need like specific assumptions on the matrix B. All right, so I promise not to be too technical, but actually the next slide is quite technical. So I will show it now, but then I will actually comment on it so that we can have a better understanding. So this is the result that was proven in collaboration with Michael and Christian, actually was published in 2018. So in this paper, we had an appendix, which was quite a technical appendix at the end of the paper, where we wrote the assumptions needed on the eigenvectors of the matrix A to be able to reduce it in upper triangular form, okay, so that we can do the upper triangularization. For the sake of simplicity, I've stated the theorem here, already assuming that A is upper triangular, but just be aware that the result can be stated in more generality. Okay, so if we have this system, then if we assume that the entries of the matrix B, so the entries B, I, J, are of order J minus I when I is bigger than J, then we can prove an isotropic Sobolev well-posedness for every Sobolev order S, which basically means what I've written down here. So if the initial data U0k is of order S plus k minus 1, and the right-hand side F as entries Fk also of order S plus k minus 1, then I will find a unique Sobolev solution U of the system with entries UK of the same Sobolev order. And clearly, because I can do this for every Sobolev order, then I can conclude that I have also C-infinity well-posedness. Okay, so, but in practice, how does this result look like? So how can I formulate these Levy conditions? So let's work on an example. So let's assume, for simplicity, that we have a matrix of order 4, but clearly I could write this for every order M. So the Levy conditions written in the theorem tells us that this is a matrix of zero-order pseudo-differential operators, and indeed, above on the diagonal and above, it is fine to have zero order. But then if I look at the parallel lines that are below the diagonal, in order to get Sobolev well-posedness, I need to require a little bit more of regularity in terms of pseudo-differential operator order, which means that on the blue diagonal, I need one order less, minus 1. On the green diagonal, I need 2 order less, minus 2, and then I end up with a minus 3 for the last entry. And you can think that in general, you will go from 0 to order minus m plus 1. So why this? You can ask why I need this. Well, going through the proof, as I was saying before, basically you write your solution, you start to solve your equations, right, from the bottom one, and then you proceed one line upwards. And at the end, you will need to apply a fixed point argument. Okay, so you will need to apply the fixed point theorem. And what you want is basically that the operators that you are considering, and sometimes you have actually compositions of them, will give you operators of order 0, so that you can have a mapping property like L2 into L2, HS into HS, and then you can apply the fixed point theorem. So in order to get these mapping properties, so in order to get operators of order 0, you will realize that in their symbol, you will have a sort of composition of terms that come from the principal part, from the matrix A, and terms that come from the matrix B. So in order to get order 0 in the end, you will require these Levy conditions here. So you will require that some of these entries will not only be of order 0, but they will be of order -1, -2, and -3. So this was a result that we proven in 2018. As I said before, there was an appendix with the upper triangularization in the paper. And later on, we wanted to do a little bit of microlocal analysis. We wanted to understand propagation of singularities. And then we had a paper on that, assuming that the matrix of the principal part depends on X only. Okay, but for me, working with system has always been interesting because I thought, okay, so this is a way to approach the study of higher order equations. And this result is sort of general and works for hyperbolic system, not in Sylvester form, I mean a general hyperbolic system. So I always thought, okay, what happens if I take an M-order hyperbolic equation, I transform it into a system, and this time the system will be even a little bit easier because the matrix A is in principle is in Sylvester form. So what happens if now I apply the theorem that I showed you before? So this one. I mean, I have quite a good result here. I have quite a lot of system machinery. Can I use it for those systems coming from equations? And this is sort of a different point of view, if you want, with respect to the results that are available in the field, because I know there are very nice results, also very refined results, but they're usually valid for specific classes of equations. They are maybe valid for order 2 or order 3 equations, and they require specific conditions on the multiplicities. So I haven't found general results for M-order equations, in particular with time and space dependent coefficients. So before moving to equation, I also would like to say, so this is a little bit of publicity for what we do, that recently this result that we had on systems has been extended to the case of singular coefficients together with my current postdoc, Bolis. And in that case, because we were really working with highly irregular coefficients like distributional, so we had to work in the context of a very weak solution. But I don't have actually time to go into details, but I just wanted to let you know. All right, so let's now go to the final part of the talk, which is higher order hyperbolic equations with multiplicities. So what I will talk about is actually on a preprint that has been submitted for publication. Since that preprint, actually, we had improved our result, right? So we know now that we can actually work with time and space dependent coefficients everywhere, okay? But when we first started this kind of a research, we were not completely sure to be able to do it. So at the beginning, we decided to start from a sort of a toy model, right? And a toy model would be this M-order hyperbolic equation, where I assume that the principal part depends on time only, and the lower order terms can depend on space as well. So this simply makes our techniques a little bit easier, but we have actually discovered very recently that we could repeat the same proof with some extra technicalities, even when the principal part depends on X as well. Okay, so we have the M-order equation, we have the corresponding Cauchy problem. We assume, so I want to work under assumptions on regularity, so I want to work under the assumption that the coefficients are smooth in X and continuous in time. I will require that the eigenvalues, I mean, imagine that you do a transformation into a system, or you just compute the roots of the equation. You want that the roots are symbols of order 1 and they are real valued. And then, as I was saying before, I do the transformation into a first order system and I forget the equation, right? And I work on the system. So the question is, how do I transfer the result that I know on non-diagonalizable system to higher order hyperbolic equations? So the idea is very simple, right? So if I do the transformation into the system, if I am able to reduce the system that I have obtained into upper triangular form, then I can immediately apply the results on system that I showed you earlier. So the result obtained with Michael and Christian. But of course, I will need to check a few things. So I will need to check that I am under the assumptions that I can actually produce this upper triangularization. And if I want to use the system, I have to impose those Levy conditions. And in particular, in this case, I have to see how these Levy conditions rely to the coefficients of the equation. Because remember that in the end, I want to be able to write down a result that I can read from the equation. So I need to have a sort of a easy way to check that my Levy conditions are fulfilled. So clearly, if I do this, so this is a little bit of a philosophy if you want. So if I do this, so I do a transformation to the system, then I do another transformation, which is an upper triangularization. So it is natural to think that every time I do a transformation, I somehow restrict the family of equations that I'm dealing with. So this is something that has to be taken into consideration. However, if I have the possibility to write down conditions that I can easily check, this is definitely positive. And also, I have to be aware that there are not so many results known in the field for equations of arbitrary order M. So any kind of achievement that I can have in this area of mathematics will clearly be welcome. And also the possibility, for instance, to write down concretely examples. That's exactly what I wanted to say. So as I said in my introduction, we all quote the results of Olenek, which is clearly very, very interesting. But let's remember that the results of Olenek is only valid for equations of the second order. And here we want to have variable multiplicities of order M for any M. All right, so let's have a sketch of the proof. It's really a sketch, right? So it's not a proof, it's basically the ideas, okay? So let's assume that we start from the equation, we do the transformation into a system. And in particular, because I want to be simple and easy, I assume that the principal part depends on T only. Then I will have my matrix of pseudo-differential operators of the first order, which is written here, which is a matrix in Sylvester form. So because I have this very special form for the equation, I can think that maybe it is slightly easier to perform the upper triangularization. And that's exactly what we observed. So there is a proposition that we can state in generality. Okay, so it is possible to reduce the matrix A into upper triangular form without additional assumptions on the eigenvectors when I start from a matrix A which is in Sylvester form. And I can concretely write down what is this matrix T, which is also invertible. So in the paper, we have like the general result. So the proposition as a sort of a constructive proof, like you really write down what is the matrix T. As an example, I have written here the matrix T in for order 3 and for order 4. And it is possible to find like a sort of a recursive formula, right? To write it in general for every n. Okay, so I will make use of T in my transformation, right? And I will go back now to the system, okay, right? So I will implement the transformation U equal TV, okay? And I will now transform, instead of having a system in U, I will have a system in V. But because of how the matrix T has been defined, once I do my transformation, I will now have here a matrix P, which is of order 1, which is in upper triangular form, with the eigenvalues on the diagonal. So I have reduced my system into upper triangular form. Okay, this is clearly very nice, but I do pay this in some way. Because if my principal part now is nice and easy to handle, I unfortunately have created extra lower order terms. And this is basically what will put some restriction on the classes of equations that I will consider, okay? But I have a very precise control on these lower order terms because I know exactly what they are, because I have precise formulas here. So there is the transformation of the matrix B. There is also something coming from the transformation, some time derivative here. But I can do it, right? So I know precisely the matrices that are there. And you can expect that when you work with a matrix A, which also depends on X, then you will do something similar, but you will have some extra terms. So it's still possible, but it becomes a little bit more challenging from a technical point of view, and you will create extra lower order terms. All right. So as I was saying before, I have a precise control of these matrices, so I can write them down. I can write them down in for any order M. I know how to write the entries, so it's technical, but I can do it, okay? And now if I look at the system that I have, which is a system in V, I am in the precise format that was considered in the system, in the theorem, sorry, that I showed you. So the theorem proven in 2018. So now I can just take my theorem and I can apply it on this system. So what happens? This will give me conditions on the lower terms that I will need now to rephrase in terms of the entries of the equation. And that's exactly what I can do here. So as a first step, let's simply take the theorem, the 2018 theorem, and let's apply it to this system. This means that I will have Levy conditions of this type. Okay, these are the Levy conditions that I will express in terms of the entries of those matrices of the lower order terms. This statement is correct. So this statement gives you the C infinity well-posedness. but probably it's not like the easiest to use because I do not see the connections with the coefficients. So what you can do now is to prove a certain number of corollaries, okay? And in these corollaries, you will try to express better these conditions, these Levy conditions in terms of the entries, the coefficients of the equation. So for instance, as a corollary, we have the following. So if we assume that m-2 eigenvalues are constant, okay? They might be different, they might coincide, some of them, but they do not depend on time, okay? Then the Levy conditions can be formulated in this way. So they will tell you that these entries of the matrix T that you can write in terms of the coefficients are of order k minus m when I take dmk, and the time derivative of lambda m minus 1, which is the m minus 1 eigenvalue, is somehow related to this entry, and you have that this difference needs to be of order minus 1. Okay, so it can look a bit technical, but what you can do now is actually to test your corollary on some examples. And I believe the good thing of this approach, so the good thing of finding a Levy condition in this way, is that you get a sort of an algorithm, if you want, to actually construct examples of every order. So let's have a look at one of those. Again, for the sake of simplicity, let's take m equal to 3, okay? Let's assume that one eigenvalue is constant, for instance, c, and the other two are depending on time. So I have a coefficient at and I have a coefficient bt. And you can see here that with t varying, you can have multiplicity up to order 3, okay? And in general, for like an equation of order m, you can have multiplicities up to order n. So we take this example, okay, and we take the corollary and we write down what the Levy condition means for this equation. And we see that if the lower order terms are written in this way, okay, so I've written here all the lower order terms. So we have lower order terms of order 2, then 1, and then 0. Then the Levy conditions, basically, they give us some specific relations between these coefficients of the lower order terms and the coefficients of the principal part, if you want, or the eigenvalues. So these are conditions that are expressed in terms of equality because they come from the order of the symbols. But again, they give you the possibility to actually create in this way many examples also of a generic order m. So some conclusion. Because clearly, when we got these results, we wanted like to have an analysis, right, of the existing literature and make a comparison, right, of the pros and cons of our result. So we can conclude that, first of all, our result allows variable multiplicities of any order. There are already existing results, but usually they assume multiplicities up to order 2. In the case m equal to 2, we are able to provide examples which do not fulfill Olenik's conditions, right? Which is clearly quite a nice achievement, right? We can deal with any space dimension. So when I was looking through the existing literature, I found results, for instance, for m-order hyperbolic equations with x-dependent coefficients, but only with x in space dimension 1. And this was mainly due to the fact that the transformation of the equation into the system was not done using pseudo-differential operators, but was done using differential operators. So clearly our method has an advantage under this point of view, because we can work in any Rn. Actually, we do not even realize that we are working in Rn and not in R1. And the Levy conditions entail lower order terms of a specific type. However, this is not quite a new fact, let's say, in this kind of research, because recently there was a result, as I was mentioning, by Spagnolo and Taglialatella, where they study the C-infinity well-posedness of hyperbolic Cauchy problem of order m, but with x-dependent coefficients only. And their result was stated and proven only in space dimension 1. The conditions that they formulated were very similar to the ones that I showed you. So they were actually requiring the lower order terms to have a special decomposition with respect to the roots of the principal part. All right, so as I was saying, after actually we submitted the preprint with like some extra work, we realized that we are able to adapt our method of proof also to the more general T and X dependent cases. So we can basically assume that the matrix A depends on X2. And I believe this is actually quite a nice fact, considering that it has always been quite challenging to study hyperbolic equations with multiplicities and variable coefficients depending on time and space. And with that, I believe I've reached the end of my talk. Okay, so these are just the papers that are mentioned in the talk. So this is the last one, which is a preprint. Thank you very much for your attention. Muchas gracias. I'm gonna, okay, are there any questions? So maybe I will keep the screen shared if we need to have a look at the talk. Please.
Okay, Claudia, Professor Claudia Gareto, thank you very much for this very, very inspiring talk. So, are there any questions for Professor Claudia Gareto? Maybe in the chat, maybe in YouTube. Okay, maybe I should start, Claudia, I should start.
Yes, please. Do you want me to stop to share so that I can actually see you? Because it's a bit weird not to be able to see people. Please.
Okay, so, okay, I saw you almost have worked intensively in this topic with your co-authors. You have considered systems with multiplicities, without multiplicities. My perspective about your talk is that you cover almost all the topic. I wanted to ask, maybe for young researchers, which are the open problems that already one can find in this topic, because already you many of them.
No, I mean, there are still many open problems. Like, so for instance, if we go back to non-diagonalizable hyperbolic systems, right? So with Michael and Christian, we have studied like propagation of singularities, but only when the matrix A depends on X, not on T.
Okay.
And this is an open problem. This is something that Michael and I always thought, oh, okay, we should do this. But actually, that requires some deeper knowledge of microlocal analysis and also like implementation of new ideas. So it's not actually so straightforward, okay? So for instance, that is an open problem. And if we also want like to connect what I do with a very weak solution, the results that I've shown today may assume that the coefficients are regular, because I'm basically using the theory of pseudo-differential operator and Fourier integral operators. So what happens if the coefficients are irregular as well? So what do? I could regularize them, right? And then I get a family of problems with regular coefficients now, depending on a parameter. But then I will probably need to look at families of Fourier integral operators depending on a parameter. I will need to look at very weak solutions. So can I write can I, for instance, state those results, the recent one on M-order hyperbolic equations for equations with singular coefficients? I have no idea. Probably yes, but it will require some work.
Right. Okay. Yes, many. Okay. The perspective still is interesting, of course, for many years of research. It seems, Claudia, that our participants were very happy with your presentation, because I didn't see more questions. So, Claudia, thank you very much.
Muchas gracias por tenerme aquí, por invitarme, y estoy tengo mucha admiración por el trabajo que ustedes hacen y espero que vamos a hacer más cosas juntos en el futuro.
Muchas gracias, Claudia. Muchas gracias.
Gracias y mucha suerte. Bye. Bye. Thank you very much.
Thank you. Okay, so thank you very much to all the participants who connected this first session in the morning in Colombia. Now, the remaining part of the program will be the talk of Professor Jesus Alonso Ochoa, which actually will be at 2 p.m. in Colombian time, and 9 p.m. in Central European Summer Time. So I really suggest to the participants to connect to this very interesting talk that we are going to have here in Javeriana University. So thank you very much, and see you in 3 hours.